If you like the space and learn about its curiosities, subscribing to the channel. Thank you for your attention and enjoy the video. Imagine a star, serene and radiant, standing as a steadfast sentinel in the vast expanse of the universe. It burns steadily, its nuclear furnace converting hydrogen into helium, producing light and warmth that travels across millions of years to reach us. Yet, what if I told you that even the most stable star hides a ticking clock, a countdown to one of the most violent and awe-inspiring events in the cosmos, a supernova? A supernova is the ultimate spectacle of creation through destruction, an astronomical event so powerful that it can outshine an entire galaxy for weeks or even months. It's the death cry of a star, releasing energy on a scale that defies human comprehension. To put it simply, a supernova is the end stage of a star's life, but it's also much more than that. It's a moment where the universe itself reshapes and reinvents. Stars, those distant pinpoints of light, come in a variety of sizes, colors, and lifespans. The larger the star, the more dramatic its death. But not all stars are destined to explode in a supernova. Small and medium-sized stars, like our Sun, will end their lives quietly, shedding their outer layers to form planetary nebulas and leaving behind dense cores known as white dwarfs. The stars that explode as supernovas, however, are the true titans of the cosmos, giants with masses at least 8 times that of the Sun. But what exactly causes such an explosion? To understand this, we must first journey into the heart of a star. At its core, nuclear fusion acts as the engine, fusing lighter elements into heavier ones and releasing massive amounts of energy in the process. This energy generates outward pressure that counteracts the inward pull of gravity, keeping the star in a delicate balance. However, this balance is not eternal. Over millions to billions of years, the star exhausts its supply of fuel. When the fusion engine runs out, the balance tips, and the star begins to collapse under its own immense gravity. This collapse is where the magic happens. Depending on the mass and composition of the star, one of 2 primary types of supernovas can occur. In a Type 2 supernova, a massive star's core implodes under its own weight, creating a shockwave that tears the star apart. In a Type Ia supernova, a white dwarf in a binary star system accumulates too much mass from its companion, triggering a runaway thermonuclear explosion. Both types release an unimaginable amount of energy, more in a single moment than the Sun will emit in its entire lifetime. Supernovas are not just catastrophic, they are essential. These stellar explosions play a pivotal role in the universe's ongoing story. They forge heavy elements, scatter them across the cosmos, and trigger the formation of new stars and planets. Every atom of oxygen you breathe and every molecule of calcium in your bones owes its existence to supernovas that exploded billions of years ago. Without them, the universe would be a much simpler and less vibrant place. Historically, supernovas have captivated human imagination for centuries. Ancient astronomers documented these guest stars as sudden, brilliant points of light appearing in the night sky, rivaling the brightness of the moon. For civilizations that didn't yet understand the mechanics of the universe, these events were often seen as omens, messages from the gods, marking the beginning or end of something monumental. Today, we understand supernovas as cosmic laboratories. By studying them, astronomers unravel the secrets of star formation, galactic evolution, and even the expansion of the universe. Supernovas are also the yardsticks by which we measure cosmic distances, acting as beacons that help us map the vast, three-dimensional structure of space. As we delve deeper into the universe's mysteries, supernovas remind us of the breathtaking interplay of destruction and creation. They are the universe's way of recycling, taking the old and broken and using it to form the new and vibrant. But this is just the beginning of the story. The science behind the explosion. What happens when the balance of a star's existence tips, transforming a glowing beacon of stability into a destructive force of unimaginable magnitude? To answer this, we must dive into the very fabric of a star's anatomy, where gravity and nuclear fusion wage a ceaseless battle. A supernova is not merely an event. It is the dramatic finale of this cosmic struggle, a spectacle that showcases the fundamental forces of nature at their most extreme. At the core of a star, nuclear fusion serves as the powerhouse. For much of a star's life, hydrogen atoms collide and fuse under immense pressure and heat, forming helium and releasing energy. This energy generates outward pressure, effectively counteracting the inward pull of gravity. This equilibrium is what allows a star to shine steadily, often for millions or even billions of years. However, this balance is precarious. The larger and hotter the star, the faster it burns through its nuclear fuel. And when that fuel begins to run out, gravity starts to take over. In the case of massive stars, those destined for Type II supernovas, the fusion process progresses beyond hydrogen and helium. In their dying days, these stars fuse heavier and heavier elements in their cores, from carbon to oxygen, and eventually to iron. Here lies the critical turning point. Iron cannot be fused into heavier elements without consuming energy rather than releasing it. As iron accumulates at the core, the star can no longer sustain the outward pressure needed to counteract gravity. The result is catastrophic. Gravity, unopposed, forces the core to collapse in a fraction of a second. This collapse is not gradual. It is violent and explosive. The core's density skyrockets, crushing matter into an incredibly compact state. If the collapsing core is massive enough, it may form a neutron star, an object so dense that a sugar cube-sized piece of its material would weigh as much as a mountain. In some cases, the collapse continues further, creating a black hole, a region of space where gravity is so intense that not even light can escape. As the core collapses, the outer layers of the star fall inward as well, only to rebound outward when they slam into the ultra-dense core. This rebound sends shockwaves racing through the star, tearing it apart in a spectacular explosion. The resulting Type II supernova releases a burst of energy so powerful that it can briefly outshine an entire galaxy. To put this into perspective, the energy radiated by a single supernova in its initial seconds exceeds the combined output of the Sun over its 10 billion-year lifetime. Type I supernovas, on the other hand, follow a different script but are no less dramatic. These explosions occur in binary star systems, where a white dwarf, an incredibly dense remnant of a small to medium star, steals matter from its companion star. As the white dwarf accumulates mass, it eventually reaches a critical limit, known as the Chandrasekhar limit. At this point, the pressure at the white dwarf's core becomes so great that it triggers a runaway thermonuclear reaction. The entire star detonates in a blinding flash, leaving no remnant behind. While both types of supernovas are driven by different mechanisms, they share a common outcome: the release of vast quantities of energy, radiation, and matter into space. This outpouring includes elements such as carbon, oxygen, silicon, and even gold and uranium, elements that are crucial for the formation of planets, moons, and life itself. Without these stellar explosions, the universe would lack the complex chemistry needed to create the richness of the cosmos as we know it. Supernovas also emit powerful shockwaves that ripple through interstellar space, compressing nearby gas clouds and triggering the formation of new stars. These shockwaves are like cosmic sculptors, reshaping their surroundings and influencing the evolution of galaxies. In this way, the death of a single star can give rise to entire generations of new stars, continuing the cycle of cosmic life and death. But supernovas do more than just reshape their local environments. They are also responsible for some of the universe's most mysterious phenomena, such as gamma-ray bursts, intense flashes of gamma radiation that can last from milliseconds to minutes. While not all gamma-ray bursts are linked to supernovas, many are thought to originate from these colossal explosions, particularly those that form black holes. The science of supernovas extends beyond their immediate aftermath. By studying the light curves and spectra of supernovas, astronomers can determine their distance and composition. Type I supernovas, in particular, have become invaluable tools for measuring cosmic distances. Because these explosions follow a predictable pattern of brightness, they serve as standard candles that help map the universe and confirm its accelerating expansion, a discovery that has profound implications for our understanding of dark energy. Yet, despite all we know, many questions remain. How does the collapse of a core precisely trigger a shockwave strong enough to unbind the star? Why do some massive stars collapse directly into black holes without producing a visible explosion? And could there be other, as yet undiscovered types of supernovas lurking in the cosmos? Supernovas are not merely events. They are cosmic phenomena that bridge the realms of physics, chemistry, and astronomy. They challenge our understanding of the laws that govern the universe, pushing the boundaries of what we know and inspiring new theories to explain their mysteries. A galactic symphony. When a supernova erupts, the universe stages a light show unlike any other. For weeks or months, the dying star transforms into a celestial beacon, its brilliance visible across millions of light years. These explosions do more than mark the dramatic end of a star's life. They paint the heavens with dazzling displays of color and light, creating a galactic symphony that echoes through the cosmos. Imagine standing on Earth thousands of years ago, looking up at the night sky, and suddenly seeing a guest star, a point of light brighter than anything you've ever known. This was the experience of ancient astronomers who witnessed supernovas without the aid of telescopes. In 1054 AD, Chinese astronomers recorded such an event, describing a guest star that shone so brightly it was visible during the day for weeks. What they were observing was the birth of the Crab Nebula, a remnant of a massive stellar explosion. Today, the Crab Nebula remains one of the most studied supernova remnants, a glowing tapestry of gas and dust that reveals the beauty of cosmic destruction. The light emitted by a supernova is not just breathtaking. It is a message from the universe, carrying invaluable information about the star's life and death. When a supernova occurs, the explosion generates an enormous amount of heat and energy, causing the ejected material to glow in a range of colors. These colors are not random. They correspond to specific elements, such as hydrogen, helium, oxygen, and iron. By analyzing the light spectrum of a supernova, astronomers can determine its composition, temperature, and velocity. This process, known as spectroscopy, is like decoding the fingerprints of a star. But why do supernovas shine so brightly? The answer lies in the sheer amount of energy released during the explosion. When a star collapses, its core heats to temperatures of billions of degrees, igniting a chain reaction that produces vast amounts of light and radiation. This light is so intense that a single supernova can outshine an entire galaxy, which contains billions of stars. However, this brilliance is fleeting. As the ejected material cools and disperses, the supernova's light gradually fades, leaving behind a ghostly remnant. One of the most fascinating aspects of supernovas is their role as cosmic lighthouses. Their extreme brightness makes them visible across incredible distances, allowing astronomers to observe them in distant galaxies. In fact, some of the farthest objects ever detected in the universe are supernovas. By studying these distant explosions, scientists gain insights into the early universe, including the formation of galaxies and the behavior of dark energy. Supernovas are also responsible for creating some of the most visually stunning objects in the cosmos. Nebulae. When a massive star explodes, it ejects its outer layers into space, forming intricate and colorful clouds of gas and dust. These nebulae are illuminated by the energy from the explosion, creating ethereal shapes and patterns. The Veil Nebula, the remnants of a supernova that occurred thousands of years ago, is a prime example. Its delicate filaments of glowing gas stretch across the sky, resembling the strokes of a cosmic paintbrush. The interplay of light and matter in these remnants reveals the chaotic beauty of supernovas. The expanding shockwaves from the explosion collide with surrounding interstellar material, creating brilliant flashes of X-rays, gamma rays, and radio waves. These interactions help astronomers map the structure of the remnants and understand the processes that drive the evolution of galaxies. Throughout history, supernovas have inspired awe and wonder. In 1604, the great astronomer Johannes Kepler observed a supernova in the Milky Way, later known as Kepler's supernova. His meticulous observations marked one of the earliest scientific studies of these phenomena, bridging the gap between myth and science. Earlier, in 1572, Tycho Brahe documented another supernova, challenging the prevailing belief that the heavens were unchanging and eternal. For ancient civilizations, supernovas were often seen as divine signs. The sudden appearance of a new, brilliant star in the sky was interpreted as an omen of great change, a harbinger of disaster, or a symbol of renewal. Indigenous cultures around the world wove these celestial events into their myths and legends, assigning them profound spiritual significance. Even today, the sight of a supernova captured through a telescope can evoke a sense of connection to the vast, mysterious universe. Modern technology has taken our understanding of supernovas to new heights. Telescopes equipped with advanced sensors can detect supernovae in real time, capturing their light curves, the way their brightness changes over time. These light curves serve as a cosmic clock, revealing the timeline of the explosion and its aftermath. Supernova surveys, such as those conducted by the Hubble Space Telescope and ground-based observatories, continuously scan the skies for these fleeting events, adding to our growing catalog of stellar explosions. Despite their transient nature, the legacy of supernovas endures. Their remnants linger for millennia, lighting up the night sky and enriching the universe with heavy elements. Every twinkle of a star, every glimmer of a galaxy, carries traces of these ancient explosions. Without supernovas, the universe would be a darker, simpler place, a silent void devoid of the complexity that makes it so captivating. As we gaze at the remnants of supernovas scattered across the cosmos, we are reminded of the extraordinary interplay of destruction and creation that defines the universe. These explosions are not just the end of a star's life. They are the beginning of something new, a cosmic rebirth that shapes galaxies, stars, and even the atoms within us. In the next chapter, we will explore how supernovas, despite their violent nature, play a vital role in seeding the universe with the elements needed for life itself. A galactic symphony. When a supernova erupts, the universe stages a light show unlike any other. For weeks or months, the dying star transforms into a celestial beacon, its brilliance visible across millions of light years. These explosions do more than mark the dramatic end of a star's life. They paint the heavens with dazzling displays of color and light, creating a galactic symphony that echoes through the cosmos. Imagine standing on Earth thousands of years ago, looking up at the night sky and suddenly seeing a guest star, a point of light brighter than anything you've ever known. This was the experience of ancient astronomers who witnessed supernovas without the aid of telescopes. In 1054 AD, Chinese astronomers recorded such an event, describing a guest star that shone so brightly it was visible during the day for weeks. What they were observing was the birth of the Crab Nebula, a remnant of a massive stellar explosion. Today, the Crab Nebula remains one of the most studied supernova remnants, a glowing tapestry of gas and dust that reveals the beauty of cosmic destruction. The light emitted by a supernova is not just breathtaking. It is a message from the universe, carrying invaluable information about the star's life and death. When a supernova occurs, the explosion generates an enormous amount of heat and energy, causing the ejected material to glow in a range of colors. These colors are not random. They correspond to specific elements, such as hydrogen, helium, oxygen, and iron. By analyzing the light spectrum of a supernova, astronomers can determine its composition, temperature, and velocity. This process, known as spectroscopy, is like decoding the fingerprints of a star. But why do supernovas shine so brightly? The answer lies in the sheer amount of energy released during the explosion. When a star collapses, its core heats to temperatures of billions of degrees, igniting a chain reaction that produces vast amounts of light and radiation. This light is so intense that a single supernova can outshine an entire galaxy, which contains billions of stars. However, this brilliance is fleeting. As the ejected material cools and disperses, the supernova's light gradually fades, leaving behind a ghostly remnant. One of the most fascinating aspects of supernovas is their role as cosmic lighthouses. Their extreme brightness makes them visible across incredible distances, allowing astronomers to observe them in distant galaxies. In fact, some of the farthest objects ever detected in the universe are supernovas. By studying these distant explosions, scientists gain insights into the early universe, including the formation of galaxies and the behavior of dark energy. Supernovas are also responsible for creating some of the most visually stunning objects in the cosmos: nebulae. When a massive star explodes, it ejects its outer layers into space, forming intricate and colorful clouds of gas and dust. These nebulae are illuminated by the energy from the explosion, creating ethereal shapes and patterns. The Veil Nebula, the remnants of a supernova that occurred thousands of years ago, is a prime example. Its delicate filaments of glowing gas stretch across the sky, resembling the strokes of a cosmic paintbrush. The interplay of light and matter in these remnants reveals the chaotic beauty of supernovas. The expanding shockwaves from the explosion collide with surrounding interstellar material, creating brilliant flashes of X-rays, gamma rays, and radio waves. These interactions help astronomers map the structure of the remnants and understand the processes that drive the evolution of galaxies. Throughout history, supernovas have inspired awe and wonder. In 1604, the great astronomer Johannes Kepler observed a supernova in the Milky Way, later known as Kepler's supernova. His meticulous observations marked one of the earliest scientific studies of these phenomena, bridging the gap between myth and science. Earlier, in 1572, Tycho Brahe documented another supernova, challenging the prevailing belief that the heavens were unchanging and eternal. For ancient civilizations, supernovas were often seen as divine signs. The sudden appearance of a new, brilliant star in the sky was interpreted as an omen of great change, a harbinger of disaster, or a symbol of renewal. Indigenous cultures around the world wove these celestial events into their myths and legends, assigning them profound spiritual significance. Even today, the sight of a supernova captured through a telescope can evoke a sense of connection to the vast, mysterious universe. Modern technology has taken our understanding of supernovas to new heights. Telescopes equipped with advanced sensors can detect supernovae in real time, capturing their light curves, the way their brightness changes over time. These light curves serve as a cosmic clock, revealing the timeline of the explosion and its aftermath. Supernova surveys, such as those conducted by the Hubble Space Telescope and ground-based observatories, continuously scan the skies for these fleeting events, adding to our growing catalog of stellar explosions. Despite their transient nature, the legacy of supernovas endures. Their remnants linger for millennia, lighting up the night sky and enriching the universe with heavy elements. Every twinkle of a star, every glimmer of a galaxy, carries traces of these ancient explosions. Without supernovas, the universe would be a darker, simpler place, a silent void devoid of the complexity that makes it so captivating. As we gaze at the remnants of supernovas scattered across the cosmos, we are reminded of the extraordinary interplay of destruction and creation that defines the universe. These explosions are not just the end of a star's life. They are the beginning of something new, a cosmic rebirth that shapes galaxies, stars, and even the atoms within us. In the next chapter, we will explore how supernovas, despite their violent nature, play a vital role in seeding the universe with the elements needed for life itself. Type 1 supernova, a quiet assassin. While some supernovas roar with the fury of collapsing giant stars, others occur in near silence, a slow and methodical buildup culminating in a thermonuclear explosion. Type 1 supernovas, often called silent assassins, represent this quieter path to stellar destruction. Unlike their Type 2 counterparts, which result from the death throes of massive stars, Type 1 supernovas arise from the remnants of smaller stars, white dwarfs, and their deadly interactions within binary systems. To understand a Type 1 supernova, we first need to revisit the concept of a white dwarf. White dwarfs are the dense cores left behind after a medium-sized star, like our Sun, exhausts its nuclear fuel and sheds its outer layers. These stellar remnants are incredibly compact, about the size of Earth, but with a mass comparable to the Sun. A white dwarf is a celestial paradox, an object so dense that a teaspoon of its material would weigh tons. yet so stable that it can exist for billions of years. However, this stability has a limit. In a binary star system, where two stars orbit a common center, a white dwarf can slowly siphon material from its companion star. This transfer of matter, often hydrogen or helium, gradually increases the white dwarf's mass. As the material accumulates on the white dwarf surface, it heats up and undergoes fusion, creating a thin layer of nuclear reactions. Over time, this process pushes the white dwarf toward a critical threshold known as the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. Once this limit is reached, the white dwarf can no longer support itself against the crushing force of its own gravity. But instead of collapsing into a neutron star or black hole, as in Type II supernovas, the white dwarf undergoes a runaway thermonuclear reaction. The carbon and oxygen in its core ignite almost instantaneously, creating an explosion so powerful that it obliterates the entire star. This is a Type Ia supernova, an event that leaves no remnant behind, only a rapidly expanding cloud of gas and debris. What makes Type Ia supernovas unique is their predictability. Because they occur when a white dwarf reaches the Chandrasekhar limit, their explosions follow a consistent pattern of brightness. This consistency has made them invaluable tools for astronomers. Type Ia supernovas serve as standard candles, reliable indicators of cosmic distances. By measuring their brightness, scientists can determine how far away they are, effectively mapping the universe. In fact, the discovery of the accelerating expansion of the universe, a finding that led to the concept of dark energy, was based on observations of Type Ia supernovas. Despite their predictability, Type Ia supernovas are not entirely uniform. Recent studies have revealed variations in their brightness and composition, suggesting that factors such as the mass and chemical makeup of the white dwarf's companion star can influence the explosion. Some Type Ia supernovas, for instance, exhibit peculiar light curves or unusual elemental abundances, challenging astronomers to refine their models of these events. The role of Type Ia supernovas extends beyond distance measurement. These explosions are also prolific producers of heavy elements like iron and nickel, which are scattered into the interstellar medium. Over time, this enrichment contributes to the chemical evolution of galaxies, including the formation of rocky planets like Earth. Every iron atom in your body owes its existence to a Type Ia supernova that occurred billions of years ago, highlighting the profound impact these explosions have on the cosmos. One of the enduring mysteries of Type Ia supernovas is the exact nature of their progenitor systems. While many are thought to result from a white dwarf accreting material from a companion star, some may arise from the collision and merger of two white dwarfs. This so-called double-degenerate scenario has gained traction in recent years, supported by observations of supernovas that defy traditional models. Understanding these progenitor systems is crucial for accurately interpreting the data provided by Type Ia supernovas, particularly in the context of measuring cosmic distances and studying dark energy. The aftermath of a Type Ia supernova is equally fascinating. Unlike Type II supernovas, which leave behind dense remnants such as neutron stars or black holes, Type Ia explosions completely destroy the white dwarf. What remains is a rapidly expanding shell of gas and dust, glowing brightly as it interacts with the surrounding interstellar medium. These remnants, such as Tycho's supernova remnant, are invaluable to astronomers. By studying their composition and structure, scientists can reconstruct the events leading up to the explosion and gain insights into the physical processes that drive these powerful events. Type Ia supernovas are not just cosmic curiosities. They are vital pieces of the universe's puzzle. Their role in measuring distances, producing elements, and shaping galaxies underscores their importance in the grand scheme of things. Yet, their silent and methodical path to destruction contrasts sharply with the violent collapse of massive stars and Type II supernovas, highlighting the diversity of processes that govern the universe. Type II supernova, the violent collapse. If Type Ia supernovas are the quiet strategists of stellar destruction, Type II supernovas are the ferocious warriors, unleashing unfathomable power in a dramatic act of self-destruction. These colossal explosions mark the end of massive stars, those at least 8 times the mass of the Sun. Unlike their silent counterparts, Type II supernovas are loud, violent, and spectacular, leaving behind some of the universe's most enigmatic objects: neutron stars and black holes. At the heart of a Type II supernova lies the life cycle of a massive star. These giants spend millions of years fusing hydrogen into helium in their cores, a process that generates immense energy and outward pressure to counteract the force of gravity. But as the star ages, it runs out of hydrogen fuel. To sustain itself, it begins fusing heavier and heavier elements: helium into carbon, carbon into oxygen, and so on, forming layers like an onion. This process continues until the core is composed of iron. Iron, however, is a dead end in the chain of fusion. Unlike lighter elements, fusing iron does not release energy, it consumes it. As iron accumulates, the star faces a catastrophic dilemma. Without the outward pressure generated by fusion, gravity gains the upper hand. In less than a second, the core collapses under its own immense weight, reaching densities so extreme that electrons and protons are squeezed together to form neutrons. This core collapse is the defining moment of a Type II supernova. The core, now a dense sphere of neutrons, halts the collapse and sends a powerful shockwave outward through the star's layers. This shockwave, combined with the release of neutrinos, ghostly particles generated in staggering quantities, tears the star apart. The result is a luminous explosion that releases more energy in a few seconds than the sun will produce over its entire lifetime. This energy powers a dazzling display of light, radiation, and matter that can outshine entire galaxies. The aftermath of a Type II supernova depends on the mass of the collapsing core. If the core's mass is below a critical threshold, it becomes a neutron star, a city-sized object so dense that a single teaspoon of its material would weigh billions of tons. Neutron stars are fascinating entities, often spinning rapidly and emitting beams of radiation that sweep across space like lighthouse beams. These spinning neutron stars are known as pulsars, and their rhythmic pulses of light and radio waves make them some of the most precise clocks in the universe. For the most massive cores, even the incredible density of a neutron star cannot withstand the force of gravity. These cores collapse further, forming black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. The formation of a black hole is one of the most extreme outcomes of a Type II supernova, signaling the birth of an object that will forever alter its surroundings. Type II supernovas are also prolific creators of heavy elements. While fusion in the star's core stops at iron, the explosion itself provides the energy needed to forge elements heavier than iron, such as gold, platinum, and uranium. These elements are ejected into space, enriching the interstellar medium and becoming the raw materials for future stars, planets, and even life. The gold in your jewelry and the iodine in your body likely originated in a Type II supernova billions of years ago. One of the most famous Type II supernovas is SN 1987A, which occurred in the Large Magellanic Cloud, a satellite galaxy of the Milky Way. This explosion, observed in 1987, provided unprecedented insights into the mechanics of supernovas. Astronomers detected neutrinos from the event, confirming theoretical models of core collapse, and studied the expanding remnant to understand the distribution of elements and energy. SN 1987A remains one of the most studied supernovas in history, a cornerstone of our understanding of these cosmic phenomena. Type II supernovas also play a crucial role in shaping galaxies. Their shockwaves compress nearby clouds of gas and dust, triggering the formation of new stars. At the same time, the energy they release can drive powerful galactic winds that redistribute material and regulate star formation. This dual role makes supernovas essential architects of galactic evolution, influencing both the birth and distribution of stars. Despite our deepening knowledge, many mysteries about Type II supernovas remain. For instance, not all massive stars that reach the end of their lives explode as supernovas. Some may collapse directly into black holes without producing a visible explosion, a phenomenon known as a failed supernova. Understanding the conditions that lead to these different outcomes is a major focus of modern astrophysics. Another open question involves the role of rotation and magnetic fields in supernova explosions. Some massive stars are thought to spin so rapidly and possess such strong magnetic fields that their explosions produce highly focused jets of material. These so-called jet-driven supernovas may be responsible for some of the universe's most energetic phenomena, including gamma-ray bursts. Type 2 supernovas are among the most visually and scientifically spectacular events in the universe. They are the violent deaths of stars, but they are also the birthplaces of some of the universe's most fascinating objects and phenomena. They remind us that destruction is not the end, but a transformation, a necessary step in the cosmic cycle of death and rebirth. Have you ever looked at the sky and felt the desire to understand your place in the universe? On Beyond the Stars, every video is a window to infinity, a journey to connect you with the mystery and beauty of the cosmos. Subscribing to the channel is more than clicking a button. It's joining a movement to spread knowledge and inspire others to look at the stars with hope and curiosity. Be the light that guides others to discover the wonders of the universe. Subscribe, and let's explore the unknown together. Supernova remnants, ghosts of the past. When the fiery brilliance of a supernova fades, it leaves behind a legacy, a hauntingly beautiful structure known as a supernova remnant. These remnants are the echoes of stellar destruction, the scattered shrapnel of a once mighty star. But they are far from lifeless debris. They are vibrant, dynamic regions that hold the key to understanding the universe's ongoing story. Supernova remnants come in a variety of forms, shaped by the explosion's energy, the star's mass, and the environment in which the supernova occurred. Typically, a remnant consists of an expanding shell of gas and dust, illuminated by the energy of the explosion. Within this shell lies the core of the original star, now transformed into a neutron star, pulsar, or black hole. These remnants, while faint compared to their explosive beginnings, shine across multiple wavelengths of light: radio, optical, X-ray, and gamma-ray, revealing their complex nature to astronomers. One of the most famous supernova remnants is the Crab Nebula, born from a supernova explosion recorded by Chinese astronomers in 1054 AD. The Crab Nebula is a tangled web of glowing filaments, each strand a thread of gas ejected during the explosion. At its center lies a pulsar, a rapidly spinning neutron star emitting beams of radiation. The Crab pulsar's rhythmic flashes of light and radio waves are a stark reminder of the violent events that gave it birth. Supernova remnants are not merely passive leftovers. They are dynamic and evolving. As the shockwave from the explosion expands outward, it interacts with the surrounding interstellar medium, creating rippling waves of energy that heat and ionize the gas. These interactions produce stunning displays of color and light, as well as high-energy phenomena such as X-rays and gamma rays. By studying these emissions, astronomers can map the distribution of elements within the remnant and uncover details about the explosion that created it. The structure of a supernova remnant depends largely on the environment in which it forms. In dense regions of space, the shockwave encounters more material, creating intricate and chaotic patterns. In less dense areas, the remnant expands more uniformly, producing a spherical shell. Remnants such as Tycho's supernova remnant and Kepler's supernova remnant showcase these variations, each offering unique insights into the interplay between stellar explosions and their surroundings. Supernova remnants also serve as cosmic laboratories, where the physics of extreme conditions can be studied. The high-energy particles accelerated by the shock waves of these remnants are believed to be a source of cosmic rays, which bombard Earth and other planets. Understanding how these particles are accelerated helps scientists unravel the mysteries of high-energy astrophysics and the origins of cosmic radiation. The remnants of supernovas are more than just visual spectacles. They're critical to the life cycle of the universe. The gas and dust expelled during a supernova enrich the interstellar medium with heavy elements, seeding the formation of new stars and planets. This process, often called chemical enrichment, ensures that future generations of stars and planets are composed of the complex elements needed for life. In this way, supernova remnants are the architects of the next chapter of the cosmos. Among the most intriguing supernova remnants are those associated with black holes. When a massive star collapses to form a black hole, the surrounding material can become highly energized, producing jets of radiation that pierce through space. These remnants are less visible in optical light, but shine brightly in X-rays and gamma rays, offering a glimpse into the extreme physics of black hole formation and accretion. Even neutron stars and pulsars within supernova remnants continue to influence their surroundings. Pulsar wind nebulae, such as the one found in the Crab Nebula, are formed when the magnetic field and radiation from a pulsar interact with the surrounding gas. These nebulae are vibrant, ever-changing structures that reveal the ongoing impact of a supernova long after its initial explosion. Supernova remnants also play a role in the formation of planetary systems. The shock waves from these remnants compress nearby gas clouds, triggering the gravitational collapse needed to form new stars. These newly formed stars may retain some of the elements from the supernova, embedding the remnants of the exploded star into their planets, moons, and even potential life forms. In this way, supernova remnants bridge the past and the future, linking the death of one star to the birth of many others. Perhaps the most poetic aspect of supernova remnants is their longevity. While the light of a supernova fades after weeks or months, its remnant can persist for tens of thousands of years, serving as a cosmic monument to a singular event. These remnants are like celestial fossils, preserving the details of their explosive origins for astronomers to study. Each one tells a story, not just of its parent star, but of the universe itself. The study of supernova remnants continues to evolve with advancements in technology. Modern telescopes, equipped with sensors that detect X-rays, gamma rays, and radio waves, allow scientists to peer into the heart of these remnants, revealing their structure and composition in unprecedented detail. Space observatories such as Chandra and Hubble have captured stunning images of remnants like the Veil Nebula and Cassiopeia, showcasing their beauty and complexity. Despite these achievements, many mysteries remain. How exactly do the shock waves of supernova remnants accelerate particles to near-light speeds? What role do magnetic fields play in shaping the structure of these remnants? And how do remnants from failed supernovas differ from those of traditional explosions? Supernova remnants are more than just the leftovers of stellar death. They are engines of cosmic transformation, shaping the universe in profound ways. They remind us that even in destruction, there is creation, and that the echoes of the past continue to shape the present and future. Supernovas as cosmic alarms. Imagine a universe with no way to measure its vastness, no cosmic mile markers to map the billions of galaxies spread across unfathomable distances. Supernovas, particularly Type Ia supernovas, have become humanity's celestial alarms, blazing beacons that help us gauge the size and structure of the cosmos. These powerful explosions are more than just stellar finales. They are vital tools for unraveling the universe's greatest mysteries. In the early 20th century, astronomers struggled to determine distances beyond our galaxy. While nearby stars could be measured using parallax, a method akin to triangulation, the technique failed for more distant objects. The cosmos seemed infinite, but impenetrable. Then came the realization that certain astronomical phenomena, like Cepheid variable stars, had predictable brightness patterns, allowing astronomers to calculate their distance based on how bright they appeared from Earth. But for even greater distances, something more powerful was needed. Enter the Type Ia supernova. Type Ia supernovas are unique in their role as standard candles, because they occur when a white dwarf reaches a consistent critical mass, the Chandrasekhar limit. The explosion produces a remarkably uniform brightness. This predictable luminosity means that by comparing a Type Ia supernova's observed brightness with its intrinsic brightness, astronomers can calculate its distance with impressive precision. These explosions, visible across billions of light years, provide a reliable way to map the farthest reaches of the universe. The discovery of the standard candle property revolutionized astronomy, allowing scientists to probe the structure and scale of the cosmos. In the late 1990s, astronomers studying distant Type Ia supernovas made a startling discovery. The universe was not just expanding, but its expansion was accelerating. This revelation, awarded the Nobel Prize in Physics in 2011, introduced the concept of dark energy, a mysterious force driving the universe's rapid growth. Without the cosmic alarms provided by Type I supernovas, this groundbreaking insight might have remained hidden. But supernovas do more than measure distances. They also reveal the dynamics of cosmic expansion. By observing how the light from supernovas shifts toward the red end of the spectrum, a phenomenon known as redshift, astronomers can track the rate at which galaxies move away from us. This information is critical for understanding the history and future of the universe, from the Big Bang to its ultimate fate. The role of supernovas as cosmic alarms extends beyond Type I events. Type II supernovas, though less predictable in brightness, still provide valuable clues about the universe's structure and evolution. By studying the light curves and spectra of these explosions, astronomers can infer the chemical composition and physical conditions of distant galaxies. This data helps build a comprehensive picture of how galaxies form, evolve, and interact over billions of years. One of the most intriguing applications of supernovas is their potential to probe the nature of dark matter and dark energy. These enigmatic components make up 95% of the universe, yet their properties remain elusive. By mapping the distribution and frequency of supernovas across cosmic history, scientists hope to uncover patterns that reveal how dark matter shapes galaxies and how dark energy influences the universe's expansion. Supernovas also act as time capsules, preserving information about the early universe. When we observe a supernova billions of light years away, we are seeing an event that occurred billions of years ago due to the finite speed of light. These distant explosions offer a glimpse into the universe's past, providing insights into the first generations of stars and the conditions that prevailed shortly after the Big Bang. Another remarkable feature of supernovas as cosmic alarms is their role in identifying gravitational waves, ripples in space-time caused by massive cosmic events. When a supernova occurs, it can emit gravitational waves detectable by instruments like LIGO and Virgo. By combining gravitational wave data with observations of light and other electromagnetic signals, astronomers gain a more complete understanding of these events. This multi-messenger approach is revolutionizing astrophysics, revealing details about the universe's most extreme phenomena. Despite their reliability, supernovas are not without challenges. Variations in the environments where they occur can affect their brightness, complicating distance calculations. Dust within galaxies, for example, can dim or redden the light from a supernova, leading to errors if not accounted for. To address these issues, astronomers use sophisticated models and statistical techniques to correct for such distortions, ensuring the accuracy of their measurements. The search for supernovas has also entered a new era with the advent of advanced telescopes and automated surveys. Projects like the Zwicky Transient Facility, ZTF, and the Vera C. Rubin Observatory are designed to scan the skies for transient events, including supernovas, in real time. These technologies enable the rapid detection and analysis of thousands of supernovas each year, providing an unprecedented wealth of data for scientists to study. The future of supernova research holds exciting possibilities. As instruments become more sensitive, astronomers may discover new types of supernovas, challenging existing classifications and theories. The detection of supernovas in the earliest galaxies could shed light on the universe's infancy, while improvements in gravitational wave technology may reveal hidden aspects of supernova mechanics. With each new discovery, these cosmic alarms continue to deepen our understanding of the universe. Supernovas are not just explosions. They are the universe's way of communicating with us, signaling its vast scale, intricate structure, and mysterious forces. They remind us that even the most violent events can serve a greater purpose, illuminating the cosmos and guiding our exploration of its many wonders. Life from stardust. In the grand narrative of the universe, supernovas are not merely cataclysmic explosions. They are the architects of life itself. These stellar deaths, though violent and seemingly destructive, sow the seeds of creation. Without supernovas, the universe would lack the complex chemistry needed to form planets, oceans, and living organisms. The phrase, "we are made of star stuff," popularized by Carl Sagan, is not just poetic. It is a profound truth rooted in the physics and chemistry of supernovae. To understand the connection between supernovas and life, we must start at the atomic level. The early universe, moments after the Big Bang, was a relatively simple place. It consisted almost entirely of hydrogen and helium, with trace amounts of lithium and beryllium. These elements formed the first generation of stars, massive and short-lived, which eventually exploded as supernovas. In these fiery deaths, a cosmic alchemy occurred. The immense heat and pressure of the explosion fused lighter elements into heavier ones, creating the building blocks of the periodic table. Supernovas are the primary source of many elements essential for life. Oxygen, which forms the air we breathe and water we drink, is produced in abundance by massive stars and dispersed into space by supernova explosions. Carbon, the backbone of organic molecules, is another supernova product, as are nitrogen, sulfur, and phosphorus, all critical for biological processes. Even the iron in our blood, which enables oxygen transport, was forged in the heart of a dying star and scattered across the galaxy by its explosive demise. But supernovas do more than create these elements. They distribute them across the cosmos. When a supernova explodes, it hurls its newly forged elements into the surrounding interstellar medium, enriching it with the raw materials needed for the formation of planets and, eventually, life. These enriched regions of space, known as stellar nurseries, become the birthplaces of new stars and planetary systems. Every terrestrial planet, including Earth, owes its composition to this process of supernova enrichment. Earth itself is a testament to the legacy of supernovas. The planet's rocky crust is rich in elements like silicon, magnesium, and aluminum, all of which originated in stellar explosions. The precious metals we mine, such as gold, platinum, and silver, were formed in the most energetic types of supernovae, or their close relatives, neutron star mergers. Even the radioactive isotopes deep within Earth, which generate heat and drive tectonic activity, are the remnants of supernova nucleosynthesis. One of the most intriguing aspects of supernova-generated elements is their role in the chemistry of life. Phosphorus, for example, is a key component of DNA and ADP, the molecule that powers cellular processes. Without supernovae enriching the universe with phosphorus, life as we know it might not have been possible. Similarly, the calcium in our bones and the potassium in our cells are products of stellar alchemy, linking our biology directly to the cosmos. Supernovas also play a critical role in shaping habitable environments. Their shock waves, as they propagate through space, compress interstellar gas clouds, triggering the formation of new stars and planetary systems. This process creates the conditions necessary for the development of habitable zones, regions around stars where liquid water can exist, a prerequisite for life. Without the recycling and redistribution of elements by supernovas, the universe would be a far less hospitable place. The influence of supernovas on life is not limited to their chemical contributions. These explosions also affect the evolution of life on a planetary scale. For example, supernovas can release bursts of cosmic radiation, which might influence mutation rates in organisms, potentially driving evolutionary change. However, this radiation can also pose a threat to life. A nearby supernova could strip a planet's atmosphere or bombard its surface with harmful particles, creating both challenges and opportunities for survival and adaptation. The connection between supernovas and life extends even to the origins of life on Earth. Some scientists hypothesize that the organic molecules necessary for life's emergence were catalyzed by the energetic environments created by supernova shockwaves. These shockwaves, interacting with interstellar dust and gas, could have triggered chemical reactions that formed complex organic compounds. When these compounds were incorporated into nascent planets like Earth, they provided the raw materials for the development of life. Another tantalizing idea is the role of supernova remnants in spreading life across the galaxy. Panspermia, the hypothesis that life can travel between planets and star systems, gains credibility when considering the dynamics of supernova explosions. The powerful shockwaves of a supernova could eject debris from a planet's surface, debris that might contain microbial life, into space. This material could then travel vast distances, potentially seeding life on other worlds. The story of supernovas and life is one of profound interconnectedness. These stellar events demonstrate that the universe is not a static place, but a dynamic and evolving system. Every atom in our bodies, every breath we take, and every thought we think is part of a cosmic cycle that began in the hearts of stars. Supernovas are the bridges between the inorganic and the organic, the lifeless and the living. As we continue to explore the universe, supernovas remind us of our place within it. They are not just distant explosions. They are the architects of existence, shaping the cosmos in ways both grand and intimate. Without them, the universe would be a dark, sterile void, devoid of the complexity and beauty that makes it so extraordinary. Imagine a cosmic flash so powerful it can outshine an entire galaxy in mere seconds, unleashing more energy than the sun will produce in its 10 billion-year lifetime. These events, known as gamma-ray bursts, GRBs, are among the most extreme phenomena in the universe. Linked to some of the most massive and energetic supernovae, GRBs are not only a spectacle of destruction, but also a window into the violent processes that shape the cosmos. Gamma-ray bursts were first discovered in the late 1960s by the Vela satellites, which the U.S. government had launched to monitor nuclear explosions on Earth. Instead of detecting terrestrial detonations, these satellites captured powerful bursts of gamma radiation originating from deep space. The mystery of these flashes captivated astronomers, who spent decades unraveling their origins. Today, we understand that gamma-ray bursts are often associated with the deaths of massive stars, particularly in the formation of black holes. When a massive star collapses under its own gravity, the core may form a black hole, surrounded by a rapidly spinning disk of gas and debris. In certain conditions, powerful jets of energy are ejected along the star's rotational axis at nearly the speed of light. These jets produce intense gamma radiation, which we observe as a gamma-ray burst when one of the jets is pointed directly at Earth. Gamma-ray bursts fall into two main categories: long-duration and short-duration bursts. Long GRBs, lasting from several seconds to a few minutes, are generally linked to the collapse of massive stars and the formation of black holes, a process known as a hypernova. These bursts often occur in regions of active star formation, where young, massive stars are abundant. Short GRBs, on the other hand, last less than 2 seconds and are associated with the mergers of compact objects, such as neutron stars or a neutron star and a black hole. Both types release staggering amounts of energy, but their mechanisms and implications differ. One of the most remarkable aspects of gamma-ray bursts is their reach. Because gamma rays are the most energetic form of electromagnetic radiation, GRBs can be detected across vast cosmic distances, making them invaluable tools for studying the early universe. Some of the most distant GRBs observed date back to when the universe was less than 1 billion years old, providing a glimpse into the formation of the first stars and galaxies. Despite their utility as cosmic beacons, gamma-ray bursts also pose a potential threat to life. A nearby GRB, if directed toward Earth, could have devastating consequences. The intense burst of radiation would strip away the planet's ozone layer, exposing the surface to harmful ultraviolet light from the sun. Such an event could lead to mass extinctions and significantly alter the course of evolution. Some scientists speculate that a GRB may have contributed to one of Earth's past extinction events, though direct evidence is difficult to confirm. Yet, gamma-ray bursts are not purely destructive. Their role in the universe extends beyond their immediate impact. GRBs illuminate the deaths of stars, shedding light on the processes that govern black hole formation, jet dynamics, and the extreme conditions of the early universe. They also reveal the distribution of matter and energy on the largest scales, helping astronomers understand the structure and evolution of the cosmos. The connection between gamma-ray bursts and supernovae adds another layer of intrigue. Observations of some long-duration GRBs have revealed their association with highly energetic supernovae, often referred to as hypernovae. These events occur when the core of a massive star collapses into a black hole, releasing jets of energy that produce the GRB while simultaneously triggering an explosion that ejects the star's outer layers. The discovery of these GRB supernovae has deepened our understanding of the relationship between stellar deaths and gamma-ray bursts. The jets produced in gamma-ray bursts are extraordinary in their precision and power. Unlike the spherical explosions of most supernovae, GRB jets are highly collimated, meaning they are tightly focused into narrow beams. This concentration of energy explains why GRBs appear so bright despite their immense distances. However, it also means that only a small fraction of GRBs are visible to us, as we can only detect them when the jet is aimed directly at Earth. Studying GRBs requires cutting-edge technology. Space-based observatories such as the Swift and Fermi gamma-ray space telescopes are designed to detect and analyze these fleeting events. Swift, for instance, can pinpoint the location of a GRB within seconds, enabling ground-based telescopes to follow up and study the burst's afterglow across multiple wavelengths. This rapid response capability has revolutionized our ability to observe and understand gamma-ray bursts in real time. Despite these advancements, many mysteries remain. For example, the precise conditions that determine whether a collapsing star produces a GRB or a more typical supernova are still poorly understood. The physics of jet formation, including the role of magnetic fields and the composition of the jets, continues to challenge theorists. Additionally, the origins of short-duration GRBs, while linked to compact object mergers, raise questions about how these systems form and evolve over time. Gamma-ray bursts are not just phenomena to be studied. They are reminders of the universe's extremes. They reveal the raw power of the cosmos, where the forces of gravity, magnetism, and nuclear energy collide in spectacular ways. Yet, for all their violence, GRBs also provide a means to understand the peaceful moments that follow, how galaxies grow, how stars form, and how life emerges from the chaos of cosmic evolution. As we deepen our exploration of gamma-ray bursts, their implications stretch far beyond their initial flash of light. They challenge us to rethink our place in the universe, both as observers of its beauty and as potential witnesses to its power. For as long as humans have gazed at the stars, celestial phenomena have captured our imagination and inspired stories, myths, and scientific inquiry. Among these wonders, supernovas stand out as rare and dramatic events that challenge our understanding of the universe. Their brilliant, sudden appearance in the sky has not only shaped the course of astronomy, but also left an indelible mark on human culture and history. Long before telescopes allowed us to study these explosions in detail, supernovas were observed and recorded by ancient civilizations. One of the earliest and most famous examples comes from 1054 AD, when Chinese and Japanese astronomers noted the sudden appearance of a guest star in the constellation Taurus. This star, visible even during the day for several weeks, marked the explosion of a massive star that created the Crab Nebula. Indigenous peoples of North America may also have recorded this event, as petroglyphs depicting a bright star near a crescent moon align with its timing. Centuries earlier, in 185 AD, Chinese records described another supernova, calling it a broom star because of its sweeping brightness. These historical accounts provided the first evidence that the night sky was not immutable, challenging long-held beliefs that the heavens were perfect and unchanging. Such observations were rare but deeply impactful, often interpreted as divine signs or omens of significant events. The idea that supernovas could signal great change persisted throughout history. In 1572, Tycho Brahe observed a new star in the constellation Cassiopeia. His meticulous records of this supernova, known today as Tycho's supernova, marked a turning point in astronomy. At a time when the prevailing Aristotelian view held that the heavens were fixed and unalterable, Tycho's observations proved that celestial phenomena could emerge and evolve. His work inspired further exploration of the universe's dynamic nature, setting the stage for the scientific revolution. A few decades later, in 1604, Johannes Kepler observed another supernova in the constellation Ophiuchus. Known as Kepler's supernova, this event became the last naked-eye supernova recorded in the Milky Way. Like Tycho, Kepler's detailed records advanced the understanding of stellar phenomena, cementing the idea that the universe was far more complex and active than previously imagined. Supernovas also influenced mythology and religion. Many ancient cultures interpreted these sudden bursts of light as messages from the gods or ancestors. In Polynesian traditions, bright celestial events were often associated with navigation and guidance, linking them to exploration and survival. In other cultures, the appearance of a new star was seen as an omen, foretelling the rise or fall of leaders, the outcome of battles, or the prosperity of kingdoms. In modern times, supernovas have found a place in popular culture, where their dramatic nature resonates with themes of destruction, renewal, and mystery. They appear in literature, film, and art as symbols of cosmic power and the fragility of existence. In science fiction, supernovas are often depicted as galactic catastrophes, capable of destroying entire planets or civilizations. Movies like Star Trek and Sunshine use supernovas as central plot devices, exploring the interplay between human ambition and the overwhelming forces of the universe. The influence of supernovas extends to music, poetry, and visual art, where they evoke a sense of wonder and existential reflection. Bands like Muse and songs by artists across genres have drawn inspiration from these celestial phenomena, using them as metaphors for transformation, love, or loss. Visual artists have recreated the intricate patterns of supernova remnants, capturing their haunting beauty and chaotic symmetry. Supernovas also play a role in shaping humanity's understanding of our origins. In educational media and public outreach, they are often presented as the engines of cosmic creation, responsible for the heavy elements that make life possible. Documentaries and planetarium shows frequently highlight supernovas as pivotal events in the life cycle of the universe, bridging the gap between scientific discovery and public fascination. Perhaps the most profound cultural impact of supernovas is their ability to connect humanity to the cosmos. They remind us that we are part of a larger story, one that spans billions of years and countless galaxies. This connection is reflected in the words of astronomers and poets alike, who see in supernovas both the chaos of destruction and the promise of renewal. Despite their rarity, supernovas continue to shape our perception of the universe and our place within it. Each new discovery adds to a narrative that is both scientific and deeply human, illustrating the interplay between observation, interpretation, and inspiration. Can Earth survive a nearby supernova? Supernovas are magnificent spectacles of light and energy, but their power also raises a question that has fascinated and concerned scientists for decades. What would happen if a supernova occurred near Earth? Could our planet withstand the effects, or would it spell disaster for life as we know it? To answer this, we must consider the forces at play in a supernova and how they interact with their surroundings. First, let's define nearby. In astronomical terms, a supernova within 50 light-years of Earth is considered close enough to pose a potential threat. Beyond this distance, the intensity of the radiation and particles emitted by the explosion diminishes significantly, reducing the risk to our planet. Fortunately, no stars capable of going supernova are currently located within this danger zone. The closest candidates, such as Betelgeuse in the constellation Orion, are well outside the critical range at about 640 light-years away. However, if a massive star were to explode within the danger zone, the consequences could be profound. The primary hazards from a nearby supernova include high-energy radiation, such as X-rays and gamma rays, and the influx of charged particles known as cosmic rays. Together, these effects could disrupt Earth's atmosphere, harm life, and alter the planet's long-term climate. One of the most immediate impacts of a nearby supernova would be on Earth's ozone layer. The intense burst of gamma rays from the explosion could strip away a significant portion of this protective shield, exposing the surface to harmful ultraviolet, UV, radiation from the sun. Increased UV levels would pose a threat to life, particularly to organisms at the base of the food chain, such as plankton, which play a critical role in marine ecosystems. The influx of cosmic rays from a supernova could further compound the damage. These high-energy particles, traveling at nearly the speed of light, would collide with molecules in Earth's atmosphere, triggering chemical reactions that produce nitrogen oxides. These compounds not only deplete ozone, but can also lead to cooling of the planet's surface by reflecting sunlight away. This combination of ozone loss and atmospheric cooling could create a cascade of environmental changes, potentially disrupting ecosystems and agriculture. Evidence suggests that supernovas may have influenced Earth's history before. Some scientists hypothesize that a supernova explosion around 2.6 million years ago, located about 150 light-years away, may have contributed to the extinction of marine megafauna. Traces of the radioactive isotope iron-60, which is produced in supernova explosions, have been found in ancient seabed deposits, supporting the idea that Earth has experienced the effects of nearby supernovas in the past. While the risks are real, the likelihood of a supernova occurring close enough to Earth to cause significant harm is extremely low. The vast distances between stars in our galaxy serve as a natural buffer, protecting planets like ours from the destructive energy of these explosions. Additionally, life on Earth has proven remarkably resilient, surviving numerous mass extinction events over billions of years. Even so, astronomers keep a close watch on potential supernova candidates. Betelgeuse, a red supergiant nearing the end of its life, has drawn particular attention due to its potential to explode as a Type II supernova. Although its distance from Earth ensures that it poses no direct threat, the event would be a spectacular sight, potentially visible even during the day. Other stars, such as Eta Carinae, also have the potential to produce supernovas, but like Betelgeuse, they are far enough away to be more of a spectacle than a hazard. In addition to monitoring individual stars, scientists are exploring ways to predict supernovas. Observations of precursor phenomena, such as changes in brightness or unusual emissions from a dying star, could provide early warning signs of an impending explosion. By combining data from ground-based observatories and space telescopes, astronomers hope to refine their ability to detect and study supernovas in real time. Understanding the risks posed by supernovas also helps us appreciate the delicate balance of life on Earth. The very elements that make life possible, oxygen, carbon, nitrogen, were forged in supernova explosions, yet these same events could threaten our planet if they occurred too close. This duality underscores the intricate and interconnected nature of the cosmos. While a nearby supernova is unlikely to pose a direct threat, the study of these events reminds us of the dynamic and sometimes unpredictable nature of the universe. They challenge us to think beyond the boundaries of our planet, to consider how cosmic events shape not just the stars but the very conditions that sustain life. Betelgeuse, a supernova waiting to happen. In the constellation Orion, a red supergiant looms, glowing ominously like an ember in the night sky. Betelgeuse, one of the most famous stars in astronomy, is not only a striking celestial object, but also a ticking cosmic time bomb. At approximately 640 light-years away, Betelgeuse is nearing the end of its life and is expected to explode as a supernova, an event that promises to be as spectacular as it is scientifically significant. Betelgeuse is no ordinary star. With a radius roughly 764 times that of the Sun, it is a massive and bloated giant, teetering on the edge of gravitational collapse. Unlike smaller, more stable stars like our Sun, Betelgeuse has burned through its nuclear fuel at a prodigious rate. This rapid consumption is a hallmark of massive stars, which, despite their size, live relatively short lives, typically a few million years compared to the Sun's 10 billion-year lifespan. Betelgeuse is now in its final stages, fusing heavier elements in its core and preparing for the inevitable. The question that has captivated astronomers and the public alike is, when will Betelgeuse explode? Predicting the exact timing of a supernova is a formidable challenge. While Betelgeuse's erratic behavior, such as its recent dimming episodes, suggests instability, these fluctuations are not necessarily indicators of an imminent explosion. Some models suggest it could happen within the next 100,000 years, a blink of an eye in cosmic terms, but the event could also occur tomorrow, or even as we observe it now, with the light of its explosion still traveling to Earth. When Betelgeuse does explode, the supernova will be a once-in-a-lifetime spectacle. For weeks, it could shine as brightly as the moon, visible even during the day. The event would dominate the night sky, its brilliance outshining every other star and rivaling that of planets like Venus and Jupiter. As the light fades, Betelgeuse will leave behind a legacy in the form of a nebula, a colorful and intricate cloud of gas and dust that will continue to enrich the interstellar medium. While the explosion will be visually stunning, it will also be an extraordinary scientific opportunity. Astronomers around the world are preparing to study Betelgeuse's supernova in real time, hoping to capture the moment its light reaches Earth. Observing the event across the electromagnetic spectrum, from radio waves to gamma rays, will provide insights into the mechanics of stellar collapse, the formation of neutron stars or black holes, and the production of heavy elements. One of the most intriguing questions is whether Betelgeuse's core will collapse into a neutron star or a black hole. Given its mass, it is likely to form a neutron star, a dense, city-sized object composed almost entirely of neutrons. However, if Betelgeuse's core is massive enough, it could continue collapsing into a black hole, one of the most mysterious and extreme objects in the universe. Despite its proximity, Betelgeuse's supernova poses no direct threat to Earth. At 640 light-years away, it is far enough that the harmful radiation and particles released by the explosion will dissipate long before reaching our planet. In fact, Betelgeuse's supernova will likely be an educational rather than existential event, offering a rare chance to witness the death of a massive star and its impact on the surrounding cosmos. Betelgeuse has also captured the public imagination, becoming a star in more ways than one. Its dramatic dimming in late 2019 and early 2020 sparked widespread speculation about its impending explosion, drawing attention from both scientists and stargazers. This great dimming, as it came to be known, was eventually attributed to a massive ejection of gas and dust that temporarily obscured the star's light. Such events highlight the dynamic and unpredictable nature of Betelgeuse, keeping the world on edge for its ultimate fate. Beyond its scientific significance, Betelgeuse holds a special place in human culture. Its name, derived from the Arabic phrase Yad al-Jawza, meaning the hand of Orion, reflects its importance to ancient star watchers. As one of the brightest and most recognizable stars in the sky, it has been a focal point of myths and stories across civilizations. In modern times, its impending supernova has inspired works of fiction and fueled public interest in astronomy. The anticipation surrounding Betelgeuse's explosion underscores humanity's fascination with the cosmos. It serves as a reminder of the universe's dynamism, where even seemingly eternal stars undergo cycles of birth, life, and death. Betelgeuse's eventual supernova will not only mark the end of an extraordinary star, but also the beginning of new stars, planets, and perhaps even life, as its elements are scattered into space. As we await Betelgeuse's dramatic finale, it is worth reflecting on what this event means for our understanding of the universe. It will be a moment of unparalleled beauty and scientific discovery, a reminder of the powerful forces that shape the cosmos. In the next chapter, we will explore the intriguing connection between supernovas and the search for extraterrestrial life, examining how these explosions may influence the habitability of planets and the potential for life elsewhere in the galaxy. Supernovas and the search for alien life. Could the violent death of a star be a catalyst for life elsewhere in the cosmos? As we explore the universe in search of extraterrestrial life, supernovas emerge as both potential hindrances and facilitators of habitability. These celestial events, while destructive, play a critical role in shaping the conditions necessary for life and could even influence the existence of advanced civilizations. The first connection between supernovas and life lies in their role as cosmic element factories. Without the heavy elements created and dispersed by supernova explosions, the chemistry needed for life would not exist. Planets capable of sustaining life require a diverse array of elements to form their rocky surfaces, atmospheres, and biological systems. From carbon and oxygen to iron and phosphorus, these ingredients are direct products of stellar deaths. Supernovas distribute these elements across galaxies, enriching interstellar gas clouds that later condense into new stars and planets. This process of chemical enrichment raises intriguing questions about the potential for life beyond Earth. In regions of the galaxy where supernova activity has been high, planets formed from enriched material might have greater diversity in their chemical composition, potentially increasing the likelihood of life. Conversely, areas with sparse supernova activity may lack the necessary elements to support life, creating vast deserts in the cosmic landscape. Supernovas also influence the habitability of planets through their impact on stellar systems. The shock waves from a nearby supernova can compress interstellar gas clouds, triggering the birth of new stars and their accompanying planetary systems. This phenomenon creates opportunities for habitable zones, regions around stars where conditions are suitable for liquid water and, by extension, life. Some scientists speculate that the timing and location of supernova-triggered star formation could determine the prevalence of life in certain regions of the galaxy. However, supernovas are not unambiguously beneficial. Their immense energy can pose significant threats to nearby planets. A supernova within 50 light-years of a habitable planet could strip away its atmosphere, exposing the surface to lethal radiation and effectively sterilizing it. Even at greater distances, the influx of cosmic rays from a supernova can disrupt planetary climates, potentially leading to mass extinctions or permanent shifts in habitability. These dual effects raise the possibility that supernovas could play a role in shaping the evolutionary trajectories of alien civilizations. On one hand, the elements produced by supernovas are essential for the development of life and technology. On the other hand, the periodic occurrence of nearby supernovas could act as a filter, extinguishing life on certain planets before it has the chance to thrive. This balance of creation and destruction underscores the delicate interplay between cosmic phenomena and the conditions for life. The search for extraterrestrial intelligence, SETI, also intersects with the study of supernovas. Advanced civilizations, if they exist, might use supernovas as beacons or signals. A supernova's immense brightness and energy could serve as a natural broadcast, and it is conceivable that an advanced species might harness such an event to send messages across interstellar distances. This idea, while speculative, highlights the potential for supernovas to play a role in cosmic communication. Supernovas might also influence the detectability of alien civilizations by shaping their technological development. A civilization that survives or benefits from a nearby supernova might gain access to unique resources, such as heavy elements for advanced technologies. Conversely, a civilization too close to a supernova might struggle to recover from the environmental and biological impacts, delaying or halting its progress. One of the most tantalizing connections between supernovas and alien life is the hypothesis that these explosions could act as catalysts for panspermia, the idea that life can spread between planets and star systems. The shock waves and debris from a supernova could eject microbial life from a planet's surface into space, where it might travel vast distances to seed other worlds. While this idea remains speculative, it aligns with growing evidence that extremophiles, organisms capable of surviving extreme conditions, could endure the harsh environment of space. Supernovas also provide valuable clues in the search for habitable exoplanets. By studying the distribution and frequency of supernovas in different regions of the galaxy, scientists can identify areas where conditions might be most favorable for life. For example, the outer regions of the Milky Way, where star density is lower and supernova activity less frequent, may offer more stable environments for long-term habitability. Conversely, the crowded central regions of the galaxy, while rich in heavy elements, may be too volatile due to frequent supernova explosions. Despite their profound influence on the cosmos, the role of supernovas in the search for alien life is not fully understood. Ongoing observations and simulations aim to unravel the complex interactions between these explosions and their environments. Missions like the James Webb Space Telescope and upcoming observatories will provide new insights into the effects of supernovas on exoplanetary systems, advancing our understanding of where and how life might emerge. Supernovas are more than just stellar deaths. They are cosmic agents of change, shaping the conditions that allow life to exist and evolve. Their dual nature as creators and destroyers reflects the delicate balance of forces that govern the universe. In the search for extraterrestrial life, supernovas remind us that life itself is a product of the universe's ceaseless cycle of destruction and renewal. The role of supernovas in black hole formation. Among the most enigmatic objects in the cosmos, black holes often emerge from the ashes of massive stars that die as supernovas. These gravitational powerhouses, where matter and light are inescapably drawn, represent the extreme endpoint of stellar evolution. Understanding the connection between supernovas and black hole formation offers insights into some of the most profound mysteries of the universe. Black holes are born from the collapse of massive stars, those with masses exceeding approximately 20 times that of the Sun. These stars spend their lives fusing lighter elements like hydrogen and helium into heavier ones, generating the outward pressure needed to counteract gravity. However, this equilibrium is temporary. When the star's core becomes dominated by iron, an element that cannot release energy through fusion, the outward pressure ceases, and gravity takes over. The result is catastrophic. In a fraction of a second, the star's core collapses to an incredibly dense state. For less massive stars, this collapse halts at the neutron star stage, where neutrons resist further compression. But for the most massive stars, even this resistance is insufficient. The core continues to collapse into an infinitely dense point called a singularity, forming a black hole. Surrounding this singularity is the event horizon, the boundary beyond which nothing, not even light, can escape. Supernovas play a crucial role in this transformation. The energy released during the explosion helps eject the star's outer layers, allowing the core to collapse unimpeded. In some cases, the supernova is extraordinarily bright and energetic, signaling the birth of a black hole. However, not all black holes form with an accompanying supernova. In what are known as failed supernovas, the core collapses directly into a black hole without a visible explosion, leaving astronomers to infer their existence through indirect means, such as the motion of nearby stars or gravitational wave signals. The type of supernova and the characteristics of the progenitor star significantly influence whether a neutron star or black hole forms. Stars with masses between about 8 and 20 times that of the Sun generally produce neutron stars, while more massive stars are likely to create black holes. The exact cutoff, however, depends on factors like rotation, metallicity, the abundance of elements heavier than helium, and the influence of binary companions. These variables complicate predictions, making black hole formation one of the most challenging topics in astrophysics. One fascinating aspect of supernova-driven black hole formation is the role of rotation and magnetic fields. Rapidly spinning stars can form highly focused jets of material during collapse, creating energetic explosions called hypernovae. These hypernovae are often associated with long-duration gamma-ray bursts, as the intense jets pierce through the star's outer layers and emit gamma rays in narrow beams. Such events are among the most powerful in the universe, briefly outshining entire galaxies. The remnants of supernovae that form black holes are as intriguing as the explosions themselves. The accretion disks surrounding newly formed black holes, composed of gas and debris from the star, emit intense X-rays as the material spirals inward. These emissions, detectable by space-based telescopes, provide a window into the physics of black hole formation and growth. In some cases, the black hole's powerful gravitational pull can strip material from a nearby star, creating a binary system that emits periodic bursts of radiation. Supernova-driven black holes also have a profound impact on their environments. The gravitational influence of a black hole can shape the structure of nearby gas clouds, triggering or suppressing star formation. In some cases, black holes at the centers of galaxies grow to become supermassive, influencing the evolution of entire galactic systems. While the exact mechanisms behind this growth remain uncertain, supernovae likely play a role in seeding the initial black hole masses. The detection of gravitational waves, ripples in space-time caused by the merger of massive objects, has opened a new avenue for studying black holes formed by supernovas. Observatories like LIGO and Virgo have detected signals from the collision of stellar mass black holes, providing direct evidence of their existence and properties. These observations offer clues about the population of black holes in the universe, including their masses, spin rates, and formation histories. Despite significant progress, many questions about black hole formation remain unanswered. For instance, why do some massive stars explode as supernovas while others collapse directly into black holes? What role do environmental factors, such as the surrounding interstellar medium, play in determining the outcome? And how do black holes formed by supernovas differ from those created through other processes, such as the mergers of neutron stars? Studying supernova-driven black hole formation is not just about understanding individual objects. It is about exploring the extremes of physics. Black holes challenge our understanding of gravity, quantum mechanics, and the fundamental nature of space and time. They are laboratories for testing Einstein's theory of general relativity and probing the mysteries of the universe. As we continue to unravel the connection between supernovas and black holes, we gain a deeper appreciation for the dynamic and interconnected nature of the cosmos. These events, born from the death of stars, remind us that the universe is a place of constant transformation, where endings are not final, but are instead gateways to new beginnings. The sound of supernovas. Though supernovas explode in the silent vacuum of space, their cosmic symphonies echo in ways that we can perceive, not through sound waves, but through the data they produce. These stellar deaths emit signals across the electromagnetic spectrum, as well as gravitational waves, neutrinos, and other forms of energy. By converting these signals into sound, scientists are uncovering the hidden rhythms of the universe, turning data into music that tells the story of cosmic cataclysm. The idea of hearing a supernova begins with the physics of the explosion. When a star collapses, it generates shockwaves that ripple through its core and eject material outward at supersonic speeds. These shockwaves create pressure waves that, in theory, could produce sound if they traveled through a medium like Earth's atmosphere. However, in the vacuum of space, sound waves cannot propagate. Instead, astronomers turn to other signals, such as light and gravitational waves, to study the dynamics of these explosions. One of the most fascinating aspects of supernova sonification is the use of light curves and spectra to create audible representations. A supernova's light curve, the way its brightness changes over time, can be mapped onto a range of frequencies, producing sounds that rise and fall in pitch as the explosion evolves. Similarly, the spectra, which reveal the chemical composition of the supernova, can be transformed into harmonics, with different elements represented by distinct tones. In recent years, researchers have also used data from gravitational waves to create soundscapes of stellar collisions and collapses. Gravitational waves are ripples in space-time generated by massive objects in motion, such as the merging of neutron stars or black holes. These waves, detected by observatories like LIGO and Virgo, can be converted into frequencies within the range of human hearing. The result is a series of chirps, hums, and oscillations that represent the cosmic dance of supermassive objects. Supernovas that produce gravitational waves are especially intriguing. When a massive star collapses to form a neutron star or black hole, the asymmetrical distribution of mass can create intense bursts of gravitational energy. While listening to these signals, scientists gain insights into the internal mechanics of the explosion, the rotation of the collapsing core, and the properties of the resulting compact object. Neutrinos, nearly massless particles emitted in staggering quantities during a supernova, also contribute to the auditory experience of these events. During the collapse of a star's core, neutrinos carry away most of the energy, escaping almost instantaneously and interacting weakly with surrounding matter. By simulating their behavior and translating their energies into sound, researchers can recreate the timing and intensity of the supernova's core collapse, offering another dimension to its cosmic melody. Sonification is not just a tool for scientists. It is a powerful way to engage the public with the wonders of the universe. Turning data into sound makes complex astrophysical phenomena accessible to non-experts, allowing people to hear the universe in ways that complement visual observations. For instance, NASA's Chandra X-ray Observatory has produced auditory interpretations of supernova remnants like the Crab Nebula, transforming X-ray data into ethereal, haunting soundtracks. The use of sound also highlights patterns and details that might be missed in visual data alone. Subtle variations in a light curve or gravitational wave signal become more apparent when mapped to frequencies, enabling scientists to identify irregularities or features that warrant further investigation. This auditory approach adds a new layer of depth to the study of supernovas and their remnants. The sounds of supernovas reveal not just the violent nature of these explosions, but also their profound interconnectedness with the universe. For instance, the rhythmic pulsations of a neutron star, born from a supernova, can be heard as steady beats or hums. These pulsars, spinning with incredible regularity, emit beams of radiation that sweep across space like lighthouse beams. When translated into sound, they create a steady cadence that underscores the precision of cosmic mechanics. Even the remnants of supernovas contribute to the cosmic symphony. Expanding shockwaves interact with interstellar gas and dust, producing radio waves that can be converted into low-frequency sounds. These interactions are like echoes, reverberating long after the initial explosion, providing a sense of the supernova's ongoing influence on its surroundings. The combination of visual and auditory data offers a multidimensional perspective on supernovas. For example, in the case of SN 1987A, one of the most studied supernovas in history, sonified data has been used to illustrate how the explosion evolved over time. By layering sounds derived from light curves, spectra, and neutrino emissions, researchers have created immersive experiences that bring the dynamics of the event to life. The interplay of sound and science also inspires art and creativity. Musicians and composers have incorporated sonified supernova data into their works, creating pieces that blend the physical with the metaphysical. These compositions serve as a reminder that the universe is not only a source of scientific inquiry, but also a wellspring of inspiration. Despite the technological advances that make sonification possible, there is still much to learn from the sounds of supernovas. Future missions and observatories, equipped with more sensitive detectors, will provide richer datasets for sonification, uncovering new details about the processes that govern these explosions. As we continue to explore the auditory dimension of the universe, we may discover patterns and phenomena that challenge our understanding of the cosmos. Supernovas, though silent in space, resonate in ways that transcend the limits of human perception. Their sounds, interpreted through data, offer a unique perspective on the universe's most powerful events, connecting us to the rhythms and harmonies of the stars. Supernova surveys, the hunt for explosions. Supernovas are some of the most fleeting and extraordinary events in the universe, their brilliance lasting mere weeks or months in the vast timescale of cosmic history. Despite their ephemerality, they are key to understanding the life cycle of stars, the formation of galaxies, and the evolution of the universe. Capturing these transient phenomena has become a central focus of modern astronomy, requiring advanced technology, global collaboration, and a bit of cosmic luck. The quest to detect supernovas begins with an understanding of their rarity and unpredictability. In a galaxy like the Milky Way, supernovas are estimated to occur once every 50 years on average. However, with billions of galaxies in the observable universe, thousands of supernovas are exploding at any given moment. The challenge lies in pinpointing these events in the vast expanse of space, often in galaxies millions or billions of light years away. Modern supernova surveys are designed to overcome this challenge, using cutting-edge telescopes and automated systems to scan the skies for transient events. Ground-based observatories such as the Zwicky Transient Facility, ZTF, and the Panoramic Survey Telescope and Rapid Response System, PanSTARRS, play a crucial role in this effort. These facilities are equipped with wide-field cameras that can capture large sections of the sky in a single exposure, making it possible to monitor thousands of galaxies simultaneously. The process begins with automated image comparison. Survey telescopes take multiple images of the same region of the sky over time, looking for changes in brightness that could indicate a supernova. Advanced algorithms then compare these images pixel by pixel, identifying objects that have suddenly appeared or brightened. These candidates are flagged for further analysis, where astronomers determine whether they are indeed supernovas or other types of transient phenomena, such as variable stars or active galactic nuclei. Once a potential supernova is identified, astronomers use follow-up observations to confirm its nature and gather additional data. Spectroscopy is a key tool in this process, as it allows scientists to analyze the light from the supernova and determine its type, distance, and composition. For example, the presence of hydrogen in the spectrum indicates a Type II supernova, while its absence suggests a Type I explosion. The speed at which the ejected material expands, inferred from spectral lines, provides clues about the energy of the explosion. Space-based observatories also play a vital role in supernova detection. The Hubble Space Telescope, for instance, has captured some of the most detailed images of supernovae and their remnants, revealing intricate structures and interactions with surrounding material. The James Webb Space Telescope, with its ability to observe in the infrared spectrum, promises to uncover supernovas in regions of space obscured by dust, such as the cores of galaxies. Another exciting development in supernova detection is the use of artificial intelligence, AI. Machine learning algorithms can analyze vast datasets from surveys, identifying patterns and anomalies with remarkable speed and accuracy. AI has already accelerated the discovery of supernovas, enabling astronomers to sift through millions of observations and focus on the most promising candidates. The importance of real-time detection cannot be overstated. Capturing a supernova at the earliest stages of its explosion, when the shockwave first breaks through the star's surface, known as the shock breakout, provides invaluable insights into the physics of the event. Early observations can reveal details about the star's size, structure, and composition, as well as the mechanisms driving the explosion. Some surveys, such as the All-Sky Automated Survey for Supernovae, AUSUS-SN, are designed specifically to detect nearby supernovas. These events are particularly valuable because their relative proximity allows for detailed study across multiple wavelengths, from radio waves to gamma rays. Nearby supernovas also have the potential to shed light on phenomena, such as neutrino emissions and gravitational waves, offering a multidimensional view of stellar death. The future of supernova hunting lies in next-generation observatories like the Vera C. Rubin Observatory, which will conduct the Legacy Survey of Space and Time, LSSD. Scheduled to begin operations soon, this survey will revolutionize the study of transient phenomena, capturing detailed images of the entire visible sky every few nights. With its unprecedented sensitivity and scope, the Rubin Observatory is expected to detect tens of thousands of supernovas annually, providing a treasure trove of data for astronomers. Gravitational wave observatories such as LIGO, Virgo, and the upcoming Einstein telescope add another layer to the search for supernovas. While these facilities are primarily designed to detect the mergers of compact objects like neutron stars and black holes, they can also capture the gravitational waves produced by asymmetric core collapse supernovas. Combining gravitational wave data with traditional observations offers a more complete picture of these events, revealing their inner workings and energetic processes. Citizen science projects have also joined the hunt for supernovas. Platforms like Xoaniverse Supernova Hunters allow amateur astronomers and enthusiasts to analyze survey data, contributing to the identification of potential supernova candidates. This collaborative approach democratizes astronomy and engages the public in the exploration of the universe's most dramatic phenomena. Despite these advancements, challenges remain. Dust and gas in the interstellar medium can obscure distant supernovas, making them difficult to detect. The vastness of space also means that many supernovas occur in faint or unobservable regions, beyond the reach of current technology. However, as telescopes become more powerful and computational techniques more sophisticated, these limitations are gradually being overcome. The ongoing hunt for supernovas is not just about cataloging cosmic explosions. It is about unlocking the secrets of the universe. Each new discovery adds to our understanding of stellar evolution, galaxy formation, and the forces that shape the cosmos. By capturing the fleeting light of dying stars, astronomers are piecing together a story billions of years in the making. Supernovae in the early universe. The story of the universe's earliest supernovae is a tale of cosmic firsts. The first stars, the first explosions, and the first heavy elements that would eventually make planets and life possible. These primordial supernovae, occurring just a few 100 million years after the Big Bang, played a pivotal role in shaping the young cosmos. They triggered the formation of galaxies, seeded the interstellar medium with elements, and laid the foundation for the universe we observe today. In the immediate aftermath of the Big Bang, the universe was a relatively simple place. It was composed primarily of hydrogen and helium, with trace amounts of lithium and beryllium. The first stars, known as population 3 stars, formed from these primordial gases. Unlike modern stars, population 3 stars contained no heavier elements, as none had yet been created. These stars were massive, short-lived, and highly unstable, setting the stage for the first supernovae. When a population 3 star exhausted its nuclear fuel, it ended its life in a spectacular explosion. These early supernovae, occurring more than 13 billion years ago, were unlike anything seen in the modern universe. With masses often exceeding 100 times that of the Sun, these stars could produce hypernovae, explosions up to 100 times more energetic than typical supernovae. The immense energy of these events dispersed the first heavy elements, such as carbon, oxygen, and iron, into the surrounding environment. This process of chemical enrichment was a turning point in cosmic history. The heavy elements created in these early supernovae were the building blocks for subsequent generations of stars and planets. Without them, the universe would have remained a lifeless expanse of hydrogen and helium. These first supernovae ensured that the cosmos would become a place of complexity, diversity, and potential habitability. The shockwaves from these early supernovae also played a crucial role in the formation of the first galaxies. As the explosion's energy propagated through the interstellar medium, it compressed gas clouds, triggering the gravitational collapse needed to form new stars. Over time, these stars grouped together to create the first galaxies, which served as the structural framework of the universe. Without the contributions of early supernovae, the development of galaxies would have been delayed, fundamentally altering the timeline of cosmic evolution. Observing these primordial supernovae directly is one of the greatest challenges in astronomy. Their extreme distances, billions of light years, mean that their light has been stretched and dimmed by the expansion of the universe. However, advancements in observational technology are beginning to make the detection of these ancient events possible. The James Webb Space Telescope, JWST, with its sensitivity to infrared light, is well suited to studying the remnants of these early explosions. By analyzing the light from distant galaxies, JWST can detect the fingerprints of heavy elements created by population 3 supernovae. Simulations and theoretical models also play a vital role in understanding these ancient explosions. By recreating the conditions of the early universe, scientists can predict how population 3 stars evolved and died, as well as the characteristics of their supernovae. These models suggest that the most massive population 3 stars may have ended their lives as parent stability supernovae, a rare type of explosion in which the star is completely destroyed, leaving no remnant behind. The legacy of early supernovae extends far beyond their immediate aftermath. The elements they produced became the raw materials for everything that followed. The stars and planets of later generations, the molecules that form the basis of chemistry, and the conditions necessary for life. Even today, the chemical signatures of these first explosions are imprinted in the oldest stars in the Milky Way, providing a window into the universe's formative years. The study of early supernovae also sheds light on the broader question of cosmic evolution. By tracing the distribution of heavy elements across the universe, astronomers can reconstruct the timeline of star formation and galaxy growth. This work has revealed that the first few hundred million years after the Big Bang were a period of rapid transformation, driven in large part by the explosive deaths of the first stars. Yet many mysteries remain. For example, how did population 3 stars form in an environment with no heavy elements? How did their unique properties influence the structure of the first galaxies? And what role did their supernovae play in shaping the distribution of matter and energy in the universe? The answers to these questions are not just about understanding the distant past. They are about understanding the forces that continue to shape the universe today. The elements forged in the early universe are still present in our solar system, our planet, and our bodies. Every atom of oxygen we breathe and every molecule of iron in our blood has its origins in the nuclear furnaces of stars, many of which exploded billions of years ago. As telescopes and computational models grow more powerful, the secrets of the universe's first supernovae are beginning to emerge. These explosions, though ancient and distant, remain central to the story of the cosmos. They remind us that the universe's past is never truly gone. It lives on in the stars, planets, and life that continue to evolve. The future of supernova research. The study of supernovae is entering an exciting new era, driven by advances in technology, observational techniques, and theoretical modeling. As scientists strive to unravel the mysteries of these cosmic explosions, they are leveraging cutting-edge tools to explore their origins, mechanics, and effects on the universe. The future of supernova research promises to deepen our understanding of stellar evolution, the cosmos, and even our own existence. One of the most significant advancements in supernova research comes from next-generation observatories. The Vera C. Rubin Observatory, with its legacy survey of space and time, LSSD, is poised to revolutionize the detection and study of transient phenomena like supernovae. Scheduled to begin operations in the mid-2020s, LSSD will image the entire southern sky every few nights, capturing an unprecedented volume of data. By identifying supernovae in real time, Rubin will allow astronomers to study these events from their earliest moments, providing critical insights into the initial stages of stellar explosions. Another groundbreaking tool is the James Webb Space Telescope, JWST. With its ability to observe in the infrared spectrum, JWST is uniquely suited to studying supernovae in distant and dust-obscured regions of the universe. Infrared observations can penetrate the thick clouds of gas and dust that often surround supernova remnants, revealing details about their composition and structure. JWST is also expected to detect the faint afterglow of some of the universe's earliest supernovae, offering a glimpse into the birth of galaxies and the first heavy elements. High-energy observatories are also advancing our understanding of supernovae. The planned Athena X-ray Observatory, set to launch in the 2030s, will provide detailed observations of supernova remnants, focusing on the high-energy processes that shape their evolution. By studying the interaction between expanding shock waves and interstellar gas, Athena will shed light on the role of supernovae in galaxy formation and chemical enrichment. In addition to traditional electromagnetic observations, multi-messenger astronomy is transforming the study of supernovae. The detection of gravitational waves by observatories like LIGO, Virgo, and the future Einstein telescope offers a new way to study core collapse supernovae. Gravitational waves can reveal details about the asymmetry of these explosions, as well as the properties of the neutron stars or black holes they leave behind. Combining gravitational wave data with light and neutrino signals creates a more complete picture of these events, unlocking new insights into their inner workings. Neutrino observatories are another critical component of multi-messenger astronomy. Facilities like Super Kamiokande in Japan and the upcoming Deep Underground Neutrino Experiment, DUNE, are designed to detect the flood of neutrinos released during a supernova. Because neutrinos escape from the star's core before light does, they provide an early warning system for supernova detection. Neutrino data can also reveal the dynamics of the core collapse, offering a direct window into the processes that drive these explosions. As observational capabilities improve, theoretical models are keeping pace. Advances in computational astrophysics are enabling scientists to simulate supernova explosions with unprecedented accuracy. These simulations incorporate factors like rotation, magnetic fields, and the influence of binary companions, providing a more nuanced understanding of the conditions that lead to different types of supernovae. By comparing these models with real-world data, researchers can refine their theories and explore new possibilities, such as exotic supernovae driven by dark matter or other unknown forces. The next frontier in supernova research also includes the search for exotic types of explosions. Recent discoveries of unusual transients, such as superluminous supernovae and fast blue optical transients, suggest that the traditional classification of supernovae may be incomplete. These rare events, which are often much brighter or faster than typical supernovae, challenge existing models and hint at new physical processes at play. Another emerging area of interest is the connection between supernovae and cosmic rays. While supernova remnants have long been suspected as sources of high-energy cosmic rays, recent observations are beginning to confirm this link. Future missions, such as the proposed Cherenkov Telescope Array, CTA, aim to study the acceleration of particles in supernova remnants, shedding light on the origins of these energetic particles and their role in shaping the interstellar medium. The role of AI and machine learning in supernova research cannot be overstated. These tools are already being used to analyze the massive datasets generated by surveys, identifying supernova candidates, and extracting meaningful patterns from complex signals. As AI algorithms become more sophisticated, They will play an increasingly central role in everything from real-time detection to theoretical modeling. Beyond the scientific implications, the future of supernova research has profound cultural and philosophical significance. As we uncover the secrets of these explosions, we gain a deeper appreciation for the interconnectedness of the cosmos. Supernovae are reminders that we are part of a universe in constant flux, where creation and destruction are inseparable. The ultimate goal of supernova research is not just to understand the mechanics of these events, but to place them within the broader context of the universe's evolution. By studying the deaths of stars, we learn about the origins of galaxies, planets, and life itself. We are, in a very real sense, unraveling the story of the cosmos, one supernova at a time. The eternal mystery of the universe. Supernovas are far more than fleeting cosmic fireworks. They are windows into some of the universe's most profound mysteries. These stellar explosions not only illuminate the processes driving the cosmos, but also raise questions that challenge our understanding of physics, matter, and even the fate of the universe itself. As we advance our knowledge, supernovae continue to intersect with some of the greatest enigmas in astronomy, offering tantalizing clues but few definitive answers. How do supernovas interact with dark energy? One of the most groundbreaking discoveries in modern astronomy, dark energy, was revealed through the study of Type I supernovae. These standard candles, used to measure cosmic distances, provided the first evidence that the expansion of the universe is accelerating. Dark energy, the mysterious force driving this acceleration, remains one of the most poorly understood aspects of cosmology. While Type I supernovae have been instrumental in confirming the existence of dark energy, many questions remain. What exactly is dark energy, and how does it interact with ordinary matter? Could supernovae themselves offer insights into its nature? By refining our measurements of supernova brightness and redshift, astronomers hope to probe the subtle effects of dark energy on the universe's structure and behavior. Upcoming missions like the Euclid Space Telescope and the Nancy Grace Roman Space Telescope will play a key role in this effort, using supernovae to test theories of cosmic acceleration. Are there unknown types of supernovas? While astronomers have classified supernovae into well-defined categories, recent discoveries suggest that the universe may harbor explosions that defy current models. Superluminous supernovae, for instance, are up to 100 times brighter than typical explosions, raising questions about their energy sources. Some may involve massive stars with extreme magnetic fields, while others could be powered by the interaction between the supernova's ejecta and dense surrounding material. Another mystery lies in the so-called fast radio bursts, FRBs, intense, millisecond-long pulses of radio waves whose origins remain unclear. Some researchers speculate that FRBs could be linked to certain types of supernovae or their remnants, such as magnetars, neutron stars with ultra-strong magnetic fields. Understanding whether these enigmatic signals are related to stellar explosions could unlock new realms of astrophysics. Can supernovas explain the origin of cosmic rays? Supernova remnants have long been suspected as the primary sources of cosmic rays, high-energy particles that permeate the universe. However, the exact mechanism by which these particles are accelerated to near-light speeds remains a topic of intense debate. Observations of supernova remnants, combined with theoretical models, suggest that shock waves from the explosion may act as natural particle accelerators. Future missions like the Cherenkov Telescope Array, CTA, aim to study gamma rays produced by cosmic ray interactions, providing insights into their origins. If supernovae are indeed responsible for the bulk of cosmic rays, their role extends beyond shaping the interstellar medium to influencing planetary environments and possibly even the evolution of life. Do supernovas shape the habitability of the universe? The dual role of supernovae as creators and destroyers makes them pivotal in discussions of cosmic habitability. While their explosions enrich the universe with the elements necessary for life, their radiation can sterilize nearby planets. This raises questions about the balance between creation and destruction. How frequently do supernovae enhance the conditions for life, and how often do they hinder it? Moreover, supernova-driven phenomena like gamma-ray bursts, GRBs, pose existential risks to life across galaxies. A sufficiently close GRB could strip away a planet's ozone layer, exposing its surface to lethal levels of ultraviolet radiation. Understanding the distribution and frequency of such events is crucial for assessing the likelihood of life's persistence on Earth and elsewhere. What role do supernovas play in interstellar travel? As humanity looks to the stars, supernovae may serve as both obstacles and opportunities for interstellar exploration. On one hand, the high-energy radiation from supernova remnants could pose hazards to spacecraft, requiring advanced shielding technologies. On the other hand, supernovae create dense clouds of gas and dust that may serve as resource-rich waypoints for future missions. Additionally, supernova remnants could become navigational beacons for interstellar travel. Their bright, persistent emissions across multiple wavelengths make them ideal landmarks for mapping the galaxy. The ability to predict and understand supernova events could one day assist in charting safe and efficient routes through space. Could supernovas hold the key to new physics? The extreme conditions within supernovae offer a natural laboratory for testing the limits of known physics. The immense temperatures, pressures, and densities during a core collapse explosion provide an environment where the behavior of matter and energy may diverge from current theories. For example, supernovae could shed light on the properties of neutrinos, elusive particles that play a critical role in the explosion mechanism. Some researchers have proposed that supernovae might also reveal evidence of exotic particles, such as axions or dark matter candidates. Detecting these particles could bridge the gap between astrophysics and particle physics, offering insights into the fundamental forces that govern the universe. What is the final fate of the universe? Supernovae, as markers of stellar death, are intricately tied to the long-term evolution of the cosmos. As the universe ages, the rate of star formation will decline, and fewer supernovae will occur. Eventually, the cosmos will enter an era dominated by dim remnants, white dwarfs, neutron stars, and black holes. This degenerate era will see the last supernovae occur as the final massive stars exhaust their fuel. What follows is a cosmic quiet, where the energy from these explosions slowly dissipates, leaving a dark and cold universe. Understanding the role of supernovae in this transition helps frame our understanding of the universe's ultimate destiny, the ongoing mystery. For all we have learned, supernovae remain a source of endless intrigue. Each explosion offers a unique glimpse into the cosmos, revealing new layers of complexity and interconnectedness. They challenge our understanding of physics, inspire new questions, and connect us to the forces that shape the universe. As we continue to study these extraordinary events, supernovae remind us that the cosmos is a place of ceaseless change. They are both the end and the beginning, the creators of elements, galaxies, and even life itself. In their brilliant, fleeting light, they illuminate not only the mysteries of the stars, but the mysteries within ourselves, our origins, our existence, and our place in the infinite expanse of the universe. The cycle of cosmic evolution. The universe, in all its complexity and grandeur, is governed by cycles of creation and destruction. At the heart of these cycles are supernovas, cataclysmic events that mark both the end of a star's life and the beginning of something entirely new. This dual role as destroyers and creators places supernovas at the center of cosmic evolution, weaving them into the fabric of the universe's ongoing story. The birth of elements. Supernovas are the ultimate forges of the cosmos, producing the heavy elements that populate the periodic table. Without these explosions, the universe would remain a simple soup of hydrogen, helium, and trace amounts of lithium, the elements formed during the Big Bang. The first generations of stars, massive and short-lived, created heavier elements like carbon, oxygen, and nitrogen through nuclear fusion in their cores. When these stars exploded as supernovas, they scattered these elements into space, enriching the interstellar medium. Later generations of stars, including our Sun, formed from this enriched material, incorporating these heavier elements into their planetary systems. Earth's rocky surface, its oceans, and even the molecules of life owe their existence to this cosmic alchemy. Every atom in your body, apart from hydrogen, was created in a star and dispersed into space by a supernova. Star formation and galactic recycling. Supernovas are not just element factories. They are also key players in star formation. The shock waves from these explosions propagate through the surrounding interstellar medium, compressing gas clouds and triggering the gravitational collapse needed to form new stars. This process, often described as galactic recycling, ensures that the death of one star can give rise to many more. In this way, supernovas regulate the pace of star formation within galaxies. By dispersing gas and dust, they prevent regions from becoming overly dense, which could halt star formation entirely. At the same time, their shock waves provide the necessary conditions for new stars to emerge, maintaining a delicate balance that sustains the galaxy's evolution. The role of supernova feedback. In addition to driving star formation, supernovas exert a powerful influence on their galactic environments through a process known as feedback. The energy released during a supernova can heat surrounding gas, creating winds that sweep material out of the galaxy's core. This feedback mechanism is crucial for shaping the structure of galaxies, preventing runaway star formation in some regions while redistributing material to others. Supernova feedback also plays a role in the formation of galaxy clusters, the largest structures in the universe. By redistributing gas and influencing its cooling rate, supernovas contribute to the intricate balance of matter and energy that governs these massive systems. The emergence of planetary systems. The elements forged in supernovas are not only essential for life, but also for the formation of planets. Rocky planets like Earth require elements like silicon, magnesium, and iron, materials that are only produced in the extreme conditions of a supernova. Even the water that covers much of our planet owes its existence to the oxygen produced in these stellar explosions. The remnants of supernovas, such as nebulae, are often the birthplaces of planetary systems. These clouds of gas and dust, enriched with heavy elements, provide the raw materials for the formation of stars and planets. Observations of regions like the Orion Nebula offer a glimpse into this process, showing how supernova remnants become cradles of new worlds. Supernovas as cosmic sculptors. Beyond their immediate impact, supernovas shape the larger structures of the universe. Their shock waves and energy outflows contribute to the formation of galactic features, such as spiral arms and interstellar bubbles. These structures, in turn, influence the movement of stars, the flow of gas, and the distribution of matter within galaxies. On even larger scales, supernovas contribute to the cosmic web, the vast network of filaments and voids that define the universe's large-scale structure. By redistributing matter and injecting energy into the intergalactic medium, they play a subtle but significant role in the universe's overall evolution. The interconnected cosmos. The story of supernovas is ultimately a story of connection. These events tie together the lives of stars, the formation of planets, and the emergence of life. They demonstrate that the universe is not a collection of isolated objects, but a dynamic, interconnected system where every event influences the next. This interconnectedness is reflected in the elements that make up our bodies and the world around us. The calcium in your bones, the oxygen you breathe, and the iron in your blood are all remnants of ancient supernovas. In a very real sense, we are made of star stuff, a testament to the profound unity of the cosmos. The future of cosmic cycles. As the universe ages, the cycles driven by supernovas will gradually wind down. Star formation is expected to slow as galaxies exhaust their supplies of gas, leading to fewer supernovas and a quieter cosmos. In the distant future, the universe may become a place dominated by the remnants of stars, white dwarfs, neutron stars, and black holes, silent witnesses to the cycles that once shaped the cosmos. Yet, even in this quiet future, the legacy of supernovas will endure. The elements they created will remain, forming the building blocks of whatever comes next. The story of supernovas is not just about the stars. It is about the universe itself, its past, present, and infinite potential. Supernovas and the quest for meaning. Supernovas are more than astronomical events. They are symbols of transformation, connection, and the profound mysteries of existence. Their dual role as destroyers and creators resonates deeply with humanity's search for meaning, prompting questions that transcend science and venture into the realms of philosophy, art, and spirituality. What can these cataclysmic explosions teach us about our place in the universe? How do they reflect the nature of existence itself? Supernovas and the fragility of life. At their core, supernovas are reminders of the universe's immense power. They highlight the fragility of life in the face of forces that operate on scales far beyond human comprehension. A single supernova releases more energy in seconds than our sun will emit over its entire 10 billion-year lifespan. The radiation from such an event could sterilize planets, or even end entire ecosystems. Yet, this fragility is not a cause for despair. It is a call to appreciate the delicate balance that sustains life. The same forces that create the chaos of a supernova also give rise to the order of planetary systems and the conditions necessary for biology. This paradox, that life emerges from destruction, offers a profound perspective on the nature of existence. The cosmic perspective, supernovas challenge us to think beyond the boundaries of our planet and even our galaxy. Their immense energy and scale force us to confront the vastness of the universe and our relatively small place within it. This cosmic perspective, popularized by astronomers like Carl Sagan and Neil deGrasse Tyson, invites humility and wonder. It reminds us that while we may be insignificant in size, we are deeply connected to the cosmos. The elements created in supernovas, oxygen, carbon, iron, are the building blocks of life. Every human being, every tree, every mountain is made of material forged in the heart of a star. This connection between the microcosm and the macrocosm is a source of awe and inspiration, bridging the gap between the scientific and the spiritual. The cycle of creation and destruction. Supernovas embody one of the universe's most fundamental principles, the cycle of creation and destruction. This cycle is not unique to stars. It is a pattern that repeats across scales and contexts, from the death of galaxies to the rebirth of ecosystems on Earth. In many ways, supernovas mirror the human experience. Moments of loss and upheaval are often followed by growth and renewal. This cosmic cycle has been reflected in the myths and philosophies of cultures throughout history. Ancient civilizations saw the stars as symbols of eternity and change, incorporating celestial phenomena into their stories about life, death, and rebirth. Today, supernovas continue to inspire art, literature, and music, serving as metaphors for transformation and resilience. Supernovas as philosophical questions. The study of supernovas raises profound questions about the nature of reality. What does it mean for a star, a seemingly eternal and unchanging object, to die? How can destruction give rise to creation? These questions challenge us to think beyond simple binaries, to embrace the complexity and interconnectedness of the cosmos. Supernovas also invite reflection on the passage of time. The light from a supernova explosion may take millions or even billions of years to reach Earth, carrying with it a message from the distant past. Observing these events is like looking back in time, glimpsing moments that occurred long before humanity existed. This temporal perspective underscores the fleeting nature of our lives and the enduring legacy of cosmic events. Humanity's role in the universe. As beings capable of observing and understanding supernovas, we hold a unique place in the universe. We are not merely passive spectators. We are participants in the cosmic story. By studying supernovas, we are unraveling the mechanisms that govern the cosmos, piecing together the history of the stars, and even predicting the future of the universe. This role as cosmic explorers carries a sense of responsibility. The more we learn about supernovas and their role in the universe, the more we understand the interconnectedness of all things. This awareness can inspire actions that honor and protect the delicate systems that sustain life, both on Earth and beyond. Supernovas and the search for extraterrestrial meaning. The search for meaning in supernovas extends to the question of extraterrestrial life. If other civilizations exist, they too would observe these celestial events, perhaps interpreting them in ways similar to, or vastly different from, our own. The universality of supernovas as physical phenomena suggests a shared cosmic experience, one that transcends the boundaries of individual planets and species. Could advanced civilizations use supernovas as tools for communication or exploration? Could they have developed technologies to harness the energy of these explosions? These speculative questions remind us that the universe is full of possibilities, many of which remain beyond our current understanding. The inspiration of supernovas. Supernovas inspire not only scientific inquiry, but also creativity and imagination. They have been the subject of countless works of art, from Van Gogh's Starry Night to modern digital compositions that attempt to capture their beauty. Music, literature, and poetry often draw on the themes of light, transformation, and mystery that supernovas evoke. Even in popular culture, supernovas serve as symbols of power and renewal. Films, novels, and video games incorporate these explosions as metaphors for monumental change, underscoring their emotional and narrative resonance. The enduring mystery. Despite centuries of observation and study, supernovas remain enigmatic. Every new discovery seems to raise as many questions as it answers, challenging our understanding of physics, chemistry, and the universe itself. This sense of mystery is part of what makes supernovas so compelling. They are reminders that the cosmos is vast, complex, and full of surprises. The journey ahead. As we continue to study supernovas, we are not just learning about stars. We are exploring the fundamental nature of reality. These explosions remind us that the universe is a place of constant change, where even destruction can be a source of creation. They inspire us to look beyond our horizons, to ask questions that have no easy answers, and to seek meaning in the infinite. The challenge of observing supernovas in real time. Capturing a supernova in real time is one of the greatest challenges in astronomy. These fleeting events, occurring unpredictably across billions of light years, demand precision, technology, and sometimes a touch of serendipity. Yet, the rewards are immense. Observing a supernova as it unfolds provides critical insights into the processes that govern the universe's most powerful explosions. Why study supernovas in real time? The moment a supernova begins, it reveals secrets that cannot be gleaned from its remnants. Early observations can capture the shock breakout, the instant when the explosion's shockwave first reaches the surface of the star. This brief flash of light, lasting minutes to hours, holds clues about the star's size, structure, and the conditions surrounding its death. Additionally, real-time data is crucial for understanding the dynamics of the explosion. The rapid changes in brightness, color, and spectrum during the first hours and days reveal the physical processes at work, such as the interaction between the supernova's ejecta and surrounding material. These details are critical for refining theoretical models and classifying supernova types. The tools of real-time detection. Observing a supernova as it happens requires a combination of cutting-edge technology and global coordination. Modern telescopes equipped with wide-field cameras are the backbone of supernova surveys. These instruments, such as those used by the Zwicky Transient Facility, ZTF, and the Pan-STARRS project, can scan large sections of the sky multiple times a night, searching for new light sources. When a potential supernova is detected, follow-up observations are critical. Spectroscopic instruments analyze the light from the explosion, identifying its chemical composition and redshift, which reveals its distance. Time-sensitive observations across the electromagnetic spectrum, from radio waves to gamma rays, capture different aspects of the explosion, providing a complete picture of the event. Space-based observatories play a vital role in detecting the earliest phases of supernovae. Telescopes like the James Webb Space Telescope, JWST, and the Hubble Space Telescope are capable of observing infrared and ultraviolet light, which can penetrate dust clouds and reveal details that are invisible to ground-based instruments. These telescopes often provide complementary data, allowing astronomers to study supernovae in greater detail than ever before. The role of automation and AI. The vastness of the sky and the sheer number of potential transient events make manual detection of supernovae impractical. Automation and artificial intelligence, AI, have transformed the field, enabling astronomers to process enormous datasets and identify supernova candidates with remarkable speed. Machine learning algorithms are particularly adept at distinguishing genuine supernovae from other transients, such as variable stars or artifacts in telescope data. These systems can analyze patterns in light curves and spectra, flagging events that match the profiles of known supernova types. By automating this process, astronomers can focus their efforts on the most promising candidates, increasing the efficiency of real-time detection. AI also plays a role in predicting supernovae. By analyzing long-term observations of stars nearing the end of their lives, algorithms can identify subtle changes in brightness or behavior that may signal an impending explosion. This predictive capability, while still in its infancy, could one day allow astronomers to capture supernovae at the precise moment they begin. Coordinating a global effort. The ephemeral nature of supernovae demands a global approach. Once a supernova is detected, astronomers around the world mobilize to observe it across multiple wavelengths and timescales. Networks like the global relay of observatories watching transients happen, growth, coordinate observations among telescopes in different locations, ensuring continuous coverage of the event. Citizen science also plays a role in this effort. Platforms like Zooniverse Supernova Hunters invite amateur astronomers to sift through survey data, helping to identify new supernova candidates. This collaborative approach not only expands the reach of professional surveys, but also engages the public in the excitement of scientific discovery. Overcoming challenges. Despite these advancements, observing supernovas in real time is fraught with challenges. The unpredictable nature of these explosions means that astronomers must constantly monitor the skies, often capturing only a fraction of the events that occur. Additionally, the light from supernovae can be obscured by interstellar dust or outshone by nearby stars, making detection difficult. Another challenge is the sheer volume of data generated by modern surveys. Projects like LSSD, which will capture petabytes of data annually, require sophisticated systems for storage, processing, and analysis. Ensuring that no supernova goes unnoticed in this deluge of information is a major priority for astronomers. The future of real-time supernova observation. The next generation of observatories promises to revolutionize real-time supernova detection. The Vera C. Rubin Observatory, set to begin operations in the near future, will scan the sky with unprecedented depth and frequency, capturing tens of thousands of supernovae each year. Its Legacy Survey of Space and Time, LSSD, will provide a continuous stream of data, enabling astronomers to study supernovae in greater detail than ever before. Other upcoming missions, such as the Nancy Grace Roman Space Telescope, will complement ground-based surveys by observing distant supernovae in the infrared, revealing events from the early universe. These observations will shed light on the first generations of stars and the role of supernovae in cosmic evolution. The human element. While technology and automation are critical, the human element remains central to the study of supernovas. Astronomers interpret data, refine models, and ask the questions that drive discovery. The thrill of capturing a supernova in real time, of witnessing the death of a star and the birth of its legacy, continues to inspire the pursuit of knowledge. The ephemeral beauty of the cosmos. Real-time observation of supernovae is a reminder of the transient nature of the universe. These events, brief yet monumental, encapsulate the beauty and impermanence of cosmic phenomena. Each supernova is a fleeting beacon, a moment of brilliance in the vast, unchanging darkness of space. Supernovas as a source of artistic inspiration. From the moment ancient humans first looked to the heavens, supernovas have inspired awe, wonder, and creativity. Their sudden brilliance, rivaling the light of the moon or even the sun, has left indelible marks on human culture, from mythology and religion to art, literature, and music. As some of the most dramatic and unpredictable events in the cosmos, supernovas continue to ignite the imagination, serving as metaphors for transformation, power, and the mysteries of existence. Ancient interpretations, omens, and myths. For ancient civilizations, the sudden appearance of a new star in the sky was both awe-inspiring and unsettling. Supernovas, visible for weeks or months before fading away, were often interpreted as divine messages or omens. In 1054 AD, Chinese and Japanese astronomers recorded a guest star that was visible during the day for weeks. This event, the supernova that created the Crab Nebula, was also likely observed by Native American cultures, as suggested by petroglyphs depicting a bright star near the moon. In many cultures, celestial phenomena were woven into mythology. Supernovas were often seen as signs of cosmic battles, the death of gods, or the birth of new ones. In Polynesian traditions, the stars were believed to guide navigators and connect the physical and spiritual worlds, and sudden changes in the night sky carried deep significance. These interpretations highlight the universal human tendency to seek meaning in the cosmos. The Renaissance and the birth of modern astronomy. The study of supernovas during the Renaissance marked a turning point in both science and art. Tycho Brahe's meticulous observations of the supernova of 1572, now known as Tycho's supernova, challenged the prevailing belief in an immutable celestial realm. His work inspired artistic depictions of the cosmos that emphasized its dynamism and complexity, reflecting the era's revolutionary ideas. In 1604, Johannes Kepler documented another supernova, Kepler's supernova, which further cemented the idea that the heavens were not static but constantly evolving. This period saw a blending of science and art, with celestial events influencing the works of philosophers, writers, and painters who sought to capture the universe's grandeur. Supernovas in literature. Supernovas have long served as literary symbols, representing themes of destruction, rebirth, and the passage of time. In science fiction, they are often portrayed as harbingers of galactic change or tools of cosmic engineering. Arthur C. Clarke's short story The Star uses a supernova as a poignant symbol of sacrifice and discovery, blending scientific wonder with human emotion. In modern literature, supernovas often function as metaphors for personal or societal upheaval. They symbolize moments of transformation, where the old gives way to the new in a blaze of brilliance. Their fleeting nature resonates with themes of impermanence and renewal, making them a powerful tool for storytelling. Visual art, capturing celestial drama. Supernovas have inspired visual artists to depict the cosmos's explosive beauty. From the swirling patterns of nebulae to the radiant colors of stellar remnants, these events provide endless inspiration. Works like Van Gogh's Starry Night capture the emotional impact of the night sky, evoking the awe and mystery that supernovas embody. Modern digital art, fueled by data from observatories like Hubble and Chandra, brings supernova remnants to life with stunning accuracy and creativity. Artists use imagery from space telescopes to create detailed representations of nebulae like the Crab Nebula and Cassiopeia A, showcasing the intricate structures formed by these cosmic explosions. These works bridge the gap between science and aesthetics, making the universe's wonders accessible to a wider audience. Music, the sound of the stars. The emotional resonance of supernovas extends to music, where composers and musicians have drawn inspiration from their cosmic drama. Classical pieces like Gustav Holst's The Planets evoke the majesty of the heavens, while contemporary artists use supernova-inspired themes to explore ideas of transformation and power. Sonification, the process of converting astronomical data into sound, has added a new dimension to the musical interpretation of supernovas. By mapping light curves, spectra, and other data to frequencies, scientists and artists create compositions that capture the rhythm and energy of these events. These works not only highlight the beauty of the cosmos, but also make complex scientific phenomena more accessible. Film and media. Supernovas in popular culture. In film and television, supernovas are often depicted as pivotal events, driving narratives of catastrophe or renewal. From the destructive power of a supernova in Star Trek to its role in forging new worlds in Interstellar, these explosions are a staple of science fiction. Their dramatic nature makes them ideal symbols for the unpredictable and transformative forces of the universe. Supernovas also feature in educational media, where their scientific and philosophical implications are explored. Documentaries like Cosmos use stunning visuals and poetic narration to explain the life cycles of stars, emphasizing the connection between supernovas and the elements that make up life. Poetry and philosophy, reflecting on the infinite. Poets and philosophers have long drawn on celestial imagery to explore existential questions, and supernovas are no exception. These events, which occur on scales of time and space far beyond human experience, invite reflection on mortality, impermanence, and the interconnectedness of all things. In his writings, Carl Sagan often likened the atoms in our bodies to star stuff forged in the fiery deaths of stars. This idea resonates with philosophical traditions that emphasize humanity's place within the larger cosmos. Supernovas remind us that we are not separate from the universe, but a part of its ongoing evolution. Art and science, a shared journey. The enduring appeal of supernovas lies in their ability to bridge the gap between art and science. Both disciplines seek to understand and interpret the universe, whether through observation or imagination. Supernovas, with their explosive beauty and profound implications, inspire collaboration between scientists, artists, and storytellers, enriching our collective understanding of existence. The timeless inspiration of supernovas. As humanity continues to explore the cosmos, supernovas remain a source of endless wonder. They challenge us to think beyond our horizons, to imagine the unimaginable, and to find meaning in the universe's grand cycles of creation and destruction. Through art, literature, music, and philosophy, these celestial events connect us to the infinite, reminding us of the beauty and mystery that lie beyond our world. Supernovas as cosmic clocks. Time, as we experience it, is fleeting and finite, yet the cosmos operates on scales that defy human comprehension. Supernovas, with their brilliant but short-lived explosions, provide a unique perspective on time, serving as cosmic clocks that mark pivotal moments in the universe's history. From the birth of galaxies to the expansion of the cosmos, these stellar events are not just astronomical phenomena, but also milestones that help us navigate the vast temporal landscape of the universe. The lifespan of a supernova. The life of a supernova is ephemeral on cosmic timescales, lasting mere weeks to months in visible light. However, its remnants, nebulae, neutron stars, or black holes, can persist for thousands to millions of years, acting as enduring markers of the explosion. By studying these remnants, astronomers can estimate when the supernova occurred and trace its effects on the surrounding interstellar medium. The progression of a supernova's light curve, the way its brightness changes over time, provides a precise clock for understanding the explosion's dynamics. Type I supernovas, for instance, exhibit highly predictable light curves, making them invaluable tools for measuring time across cosmic distances. This reliability has made them the cornerstone of efforts to map the expansion of the universe. Supernovas and the measurement of cosmic time. Supernovas have revolutionized our understanding of the universe's age and evolution. Type I supernovas, as standard candles, allow astronomers to measure the distances to faraway galaxies with remarkable accuracy. By combining these distance measurements with the redshift of the galaxies, the stretching of light due to the universe's expansion, scientists can calculate how fast the universe is growing. These observations led to the groundbreaking discovery of dark energy, the mysterious force driving the universe's accelerating expansion. By studying supernovas at various redshifts, astronomers have pieced together a timeline of cosmic history, from the Big Bang to the present day. Supernovas serve as both markers of the past and indicators of the universe's future trajectory. Supernovas and the early universe. The light from the earliest supernovas provides a glimpse into the first billion years of the universe's history. These explosions, occurring in the first generations of massive stars, seeded the cosmos with heavy elements and shaped the formation of galaxies. Observing these ancient events, whose light has traveled billions of years to reach us, is like peering into a cosmic time capsule. The challenge of detecting these early supernovas lies in their faintness and distance. However, advancements in infrared astronomy, particularly with the James Webb Space Telescope, JWST, are enabling scientists to study these primordial explosions. By analyzing the light from these events, astronomers can reconstruct the timeline of the universe's early development and the role of supernovas in shaping it. Supernovas and the galactic clock. Within galaxies, supernovas play a critical role in regulating the cycles of star formation and chemical enrichment. The frequency of supernovas in a galaxy reflects its stage of evolution. Younger, star-forming galaxies experience frequent supernova explosions, while older, quiescent galaxies see fewer such events. By studying the distribution and timing of supernovas in different types of galaxies, astronomers can piece together the story of galactic evolution. For example, the Milky Way's history is written in the remnants of its past supernovas. These remnants reveal periods of intense star formation and the movement of material across the galaxy, providing a timeline of its dynamic past. Supernovas and the life cycles of stars. On a smaller scale, supernovas are key markers in the life cycles of stars. Massive stars that end their lives as supernovas follow a predictable sequence of stages, from their birth in stellar nurseries to their explosive deaths. By observing stars at various points in this cycle, astronomers can construct detailed models of stellar evolution. Supernovas also leave behind enduring legacies in the form of neutron stars and black holes. The rotation rates and magnetic fields of neutron stars, for instance, provide clues about the timing and mechanics of their parent star's explosion. These remnants act as clocks that continue ticking long after the supernova's light has faded. Supernovas and the passage of time on Earth. Supernovas have even influenced the history of our planet. Traces of radioactive isotopes, such as iron-60, found in deep-sea sediments suggest that nearby supernova explosions occurred within the past few million years. These events may have affected Earth's atmosphere and climate, leaving subtle imprints on the planet's geological record. By studying these isotopic signatures, scientists can estimate when these nearby supernovas occurred and their potential impact on Earth. This connection between cosmic events and terrestrial history highlights the interconnectedness of the universe and the role of supernovas as markers of time on both cosmic and planetary scales. Supernovas as philosophical timekeepers. The fleeting brilliance of a supernova is a poignant reminder of the impermanence of all things, from stars to civilizations. Yet, their remnants endure, influencing the cosmos long after their light has faded. This duality of ephemerality and legacy mirrors the human experience, where moments of brilliance are followed by enduring impacts. Supernovas challenge us to think about time in new ways, beyond the linear progression of seconds, minutes, and years. They remind us that the universe operates on scales of time that stretch far beyond human lifespans, yet their light connects us to events that occurred billions of years ago. In this way, supernovas link the past, present, and future in a continuous cosmic narrative. The timeless inspiration of supernovas. As cosmic clocks, supernovas serve as benchmarks for understanding the universe's history and evolution. They teach us about the passage of time on scales both grand and minute, offering perspectives that are both humbling and awe-inspiring. Each explosion, though brief, leaves a legacy that echoes across space and time, reminding us of the dynamic and ever-changing nature of the cosmos. Supernovas and the future of exploration. As humanity advances its understanding of the cosmos, supernovas emerge not only as subjects of study, but also as potential influences on future exploration and technology. These stellar explosions, with their immense energy and transformative effects, may one day play a role in guiding humanity's interstellar ambitions, offering resources, landmarks, and even opportunities to harness the universe's power. Supernovas as navigational beacons. Interstellar travel requires precise navigation across vast distances, and supernova remnants, bright, persistent sources of radiation across multiple wavelengths, could serve as invaluable navigational aids. Pulsars, rapidly spinning neutron stars left behind by supernovas, emit highly regular bursts of radiation that can function as natural cosmic lighthouses. By cataloging pulsars and their emissions, astronomers are developing a celestial navigation system similar to GPS, but on a galactic scale. Spacecraft equipped with sensitive detectors could use the timing of pulsar signals to triangulate their position within the Milky Way, enabling accurate interstellar travel. This pulsar map would allow explorers to navigate with unparalleled precision, even in the vast emptiness of space. Supernova remnants as resource deposits. The remnants of supernovas are rich in heavy elements, such as gold, platinum, and uranium, created during the explosion. As humanity ventures further into space, these resources could become critical for constructing advanced technologies and sustaining interstellar missions. Mining operations on asteroids or planetary systems enriched by nearby supernovae might provide the raw materials needed for space habitats, propulsion systems, and more. In addition to heavy elements, supernova remnants contain vast amounts of gas and dust, which could be used to refuel spacecraft or support the development of life support systems. Harnessing these resources would require innovative technologies, but the potential rewards are immense. Supernovas and energy harvesting. The energy released during a supernova is staggering, dwarfing anything humanity can currently generate. While capturing the energy of an active supernova is beyond today's technological capabilities, future advancements might allow for the harnessing of the energy emitted by remnants, such as pulsars or accretion disks around black holes. One speculative concept involves the use of Dyson swarms, arrays of solar collectors, to harvest the radiation emitted by neutron stars or black holes formed by supernovae. This energy could power interstellar colonies or spacecraft, providing a virtually limitless energy source for humanity's expansion into the cosmos. Supernova shockwaves and terraforming. The shockwaves from supernovae, which compress interstellar gas clouds, play a role in triggering star formation and shaping planetary systems. In the distant future, humanity might learn to manipulate these shockwaves to influence the conditions within interstellar environments. For instance, controlled interaction with shockwaves could accelerate the formation of stars or planets in targeted regions, enabling the creation of habitable systems. Terraforming efforts on planets with thick atmospheres or dense clouds might also benefit from the energy and radiation produced by nearby supernova remnants. While speculative, these ideas highlight the transformative potential of understanding and utilizing supernova-driven processes. Supernovas as catalysts for exploration. The study of supernovas has already propelled advancements in technology and exploration. Instruments designed to observe these phenomena, such as X-ray telescopes and neutrino detectors, have led to breakthroughs in other fields, from medical imaging to materials science. Continued research into supernovas will likely yield innovations that benefit both space exploration and life on Earth. Additionally, the discovery of nearby supernova candidates, such as Betelgeuse, fuels public interest in astronomy and inspires investments in space technology. The anticipation of witnessing a supernova within our lifetime serves as a reminder of the dynamic and ever-changing nature of the universe, motivating humanity to explore beyond its planetary boundaries. Supernovas and interstellar communication. In the search for extraterrestrial intelligence, SETI, supernovas offer intriguing possibilities for interstellar communication. Advanced civilizations might use supernovae as natural amplifiers, timing their signals to coincide with the explosions or embedding information within the emissions of the remnants. This concept, while speculative, underscores the potential for supernovas to play a role in interstellar dialogue. Even if no extraterrestrial signals are found, studying supernova emissions could reveal unexpected phenomena, deepening our understanding of the universe and its hidden complexities. Preparing for the next supernova. The inevitability of a nearby supernova, though distant in cosmic terms, underscores the importance of preparation. Observing such an event in real time would provide unparalleled opportunities for scientific discovery, from understanding stellar death to testing theories of gravitational waves and neutrinos. The development of global networks of observatories, combined with advances in data analysis and AI, ensures that humanity will be ready to capture and analyze the next cosmic explosion. Supernovas as symbols of human potential. Beyond their scientific and technological implications, supernovas serve as symbols of humanity's capacity to explore, innovate, and adapt. They remind us that the universe is a place of boundless possibility, where even the most destructive events can inspire creation and growth. As we look to the future, supernovas encourage us to think boldly, to embrace challenges, and to seek answers to the questions that define our existence. Whether as navigational aids, energy sources, or cosmic landmarks, these stellar explosions will continue to shape the trajectory of human exploration and discovery. Supernovas and the fate of the universe. Supernovas are not just dramatic moments in the life of a star. They are integral to the story of the universe itself. These explosions bridge the cosmic past, present, and future, marking the cycles of stellar death and rebirth. But as the universe evolves, the frequency and nature of supernovae will inevitably change, raising questions about their role in the ultimate fate of the cosmos. The decline of stellar deaths. In the current era of the universe, star formation is abundant, fueled by vast reservoirs of gas and dust. Massive stars, born in these stellar nurseries, live short, fiery lives, ending in spectacular supernovae. However, this golden age of star formation will not last forever. As galaxies consume their supplies of gas, the rate of star birth, and consequently the rate of supernovae, will decline. Astronomers predict that within a few billion years, most galaxies will enter a quiescent phase, where star formation slows dramatically. The massive stars that fuel supernovae will become increasingly rare, and the universe will grow quieter, with fewer and fewer of these cosmic explosions punctuating the darkness. The era of white dwarfs and Type Ia supernovas. Even as core collapse, supernovae diminish. Type Ia supernovae, those caused by white dwarfs and binary systems, may continue to occur. These explosions are triggered by the slow accretion of material from a companion star, a process that can take billions of years. As a result, Type Ia supernovae could persist long after the era of massive star formation has ended. These supernovae will become the dominant source of stellar death, but their frequency will also decline over time. As binary systems exhaust their fuel and white dwarfs cool into inert black dwarfs, the universe will lose one of its most powerful sources of light and energy. The cosmic quiet, a universe without supernovas. In the far future, the universe will enter a phase known as the degenerate era. During this time, the only remaining stars will be long-lived red dwarfs, slowly burning their hydrogen over trillions of years. These stars, too small to end their lives as supernovae, will quietly fade into white dwarfs, leaving no dramatic explosions behind. As the last stars die out, the universe will grow increasingly dark. Without the light and energy of supernovae, galaxies will lose their dynamism, becoming silent collections of stellar remnants. The universe will shift from a place of creation and transformation to one of stillness and decay. The legacy of supernovae. Even as the universe grows darker, the legacy of supernovae will endure. The heavy elements they created will remain, locked in planets, moons, and interstellar dust. These elements, forged in the fires of dying stars, may continue to fuel new forms of complexity and evolution, even in a universe without light. Supernova remnants, such as neutron stars and black holes, will also persist, influencing their surroundings for billions or even trillions of years. These objects, though dim and silent, will continue to warp space-time, interact with other remnants, and shape the distribution of matter on cosmic scales. The long-term fate of the universe. The ultimate fate of the universe depends on factors that supernovae have helped illuminate, such as the expansion driven by dark energy. If the expansion continues to accelerate, the universe may experience a big freeze, where galaxies, stars, and eventually even atoms are torn apart by the relentless stretching of space-time. In this scenario, the contributions of supernovae to cosmic structure and chemistry will remain frozen in the vast emptiness. Alternatively, if the expansion slows or reverses, the universe could collapse in a big crunch, with all matter and energy converging into a singular point. In such a scenario, supernova remnants and their elements would be drawn back into the primordial chaos, potentially setting the stage for a new cycle of cosmic rebirth. A third possibility, known as the Big Rip, envisions a universe where dark energy becomes so dominant that even the smallest particles are torn apart. In this extreme future, the remnants of supernovae, neutron stars, black holes, and heavy elements would be destroyed, erasing the traces of these explosive events. The philosophical implications. The decline and eventual disappearance of supernovae raise profound questions about the nature of the universe and humanity's place within it. Supernovae, which have been central to the creation of life and the shaping of galaxies, are temporary phenomena, in an ever-changing cosmos. Their transience mirrors the impermanence of all things, from stars to civilizations. Yet, their legacy reminds us that even the briefest moments can have lasting impacts. The elements forged in supernovae will continue to shape the universe, serving as building blocks for whatever comes next. This persistence offers a sense of continuity, a thread that connects the universe's past, present, and future. Humanity's role in the supernova era. As intelligent observers of the universe, humans have a unique opportunity to study and appreciate supernovae during this brief window of cosmic history. Our ability to understand these events and their implications for the universe's evolution underscores the profound interconnectedness of existence. By exploring supernovae, we gain insight not only into the mechanics of the cosmos but also into our own origins. These explosions remind us that we are part of a larger story, one that began in the hearts of stars and continues in the vast expanse of space. The enduring mystery of supernovae. Even as supernovae fade from the universe, their mysteries endure. How do they interact with dark matter and dark energy? What role might they play in the evolution of intelligent life elsewhere in the cosmos? These questions, and countless others, ensure that the study of supernovae will remain a cornerstone of astronomy for generations to come. A universe without supernovas. The universe as we know it is dynamic and ever-changing, with supernovas serving as some of its most spectacular milestones. Yet, as the cosmos ages, the forces driving these explosions will fade. What would the universe look like in an era without supernovas? How would this stillness reshape our understanding of cosmic evolution? And what possibilities might arise in the silence? The waning of the stellar cycle. Supernovas are the fiery punctuation marks of the stellar life cycle, marking the deaths of massive stars and fueling the birth of new generations. Without these explosions, the cycles of star formation and chemical enrichment would come to an end. The vast clouds of gas and dust that give rise to stars would no longer be replenished with heavy elements, leaving the cosmos dominated by lighter, simpler elements like hydrogen and helium. This decline would be gradual, unfolding over billions of years. As the last massive stars explode, the universe would transition into an era of long-lived, low-mass stars like red dwarfs. These stars, while stable and efficient, do not end their lives as supernovas, instead quietly burning their fuel over trillions of years before fading into white dwarfs. The silent cosmos. In a universe without supernovas, silence would reign. The dramatic bursts of light and energy that once lit up galaxies would be replaced by the slow dimming of aging stars. The remnants of past supernovas, nebulae, neutron stars, and black holes would persist, but their interactions would become less frequent as the supply of new material dwindles. Galaxies would gradually lose their brightness and structure, evolving into collections of dark, inactive remnants. The Milky Way, for instance, might resemble a ghostly disk of white dwarfs, neutron stars, and black holes, orbiting in relative stillness. The once vibrant interplay of forces, shock waves, radiation, and stellar winds would fade, leaving a universe defined by stasis. The legacy of supernovas. Even in this quiet future, the legacy of supernovas would endure. The heavy elements they produced would remain locked in planets, moons, and other celestial bodies, continuing to shape the cosmos in subtle ways. These elements might fuel new forms of complexity, giving rise to phenomena we cannot yet imagine. For example, planetary systems around long-lived red dwarfs could persist for trillions of years, providing stable environments for life to evolve. The heavy elements forged in supernovas would be essential for the chemistry of such worlds, enabling the formation of complex molecules and potentially even biology. A universe of remnants. In a universe without supernovas, the remnants of these explosions, neutron stars, black holes, and white dwarfs, would dominate. Neutron stars, with their immense density and magnetic fields, would continue to emit radiation for billions of years, slowly fading into black neutron stars. Black holes, unaffected by the lack of supernovas, would persist as gravitational anchors, influencing the motion of nearby remnants. The interactions between these remnants might create fleeting moments of activity, such as the occasional merger of neutron stars or the accretion of matter onto a black hole. These events, while rare, would inject bursts of energy into the quiet cosmos, reminders of the universe's more dynamic past. The role of intelligent life. If intelligent life persists into this distant future, it would face a vastly different universe. The lack of new supernovas would limit the availability of certain resources, such as heavy elements needed for advanced technologies. Civilizations might rely on remnants of past supernovas, mining asteroids, or dismantling white dwarfs to extract the materials they need. In this era, the knowledge of supernovas would become a form of cosmic archaeology, a way of understanding the universe's earlier, more vibrant history. Observing the remnants of these explosions would offer insights into the forces that shape the cosmos, serving as a bridge between past and present. Speculative possibilities. While a universe without supernovas might seem static, it could also be a canvas for new and unforeseen phenomena. Long-lived civilizations might find ways to manipulate the remnants of stars, creating artificial supernovas or using black holes to generate energy. These activities could inject new dynamism into the cosmos, reshaping it in ways we cannot yet predict. Another possibility is the emergence of new physical processes in the distant future. As the universe evolves, conditions may arise that lead to phenomena entirely different from supernovas, driven by forces we do not yet understand. These processes could reignite cycles of creation and destruction, offering a new chapter in the universe's story. The philosophical implications. A universe without supernovas invites profound reflection on the nature of change and impermanence. These explosions, which once symbolized the cosmos's creative power, would become memories, their echoes lingering in the remnants they left behind. This shift from dynamism to stillness raises questions about the universe's ultimate purpose and destiny. The absence of supernovas would also challenge our understanding of beauty and meaning. Without these brilliant beacons, the cosmos might appear dark and lifeless. Yet its history, written in the stars and their remnants, would remain a testament to the forces that shaped it. The eternal mystery. Even in a universe without new supernovas, the mysteries they represent would endure. The processes that drive these explosions, the elements they create, and their role in cosmic evolution would continue to inspire curiosity and exploration. Their legacy would be a reminder of the universe's capacity for transformation, even in the face of entropy and decay. Supernovas and the end of the universe. As humanity peers deeper into the cosmos, the question of the universe's ultimate fate looms large. Supernovas, with their dual role as destroyers and creators, offer a unique lens through which to explore this profound mystery. They illuminate the forces shaping the universe's evolution and provide clues about its eventual destiny. What can these stellar explosions tell us about the end of everything, and how do they fit into the grand narrative of cosmic existence? The universe's possible futures. The universe's fate depends on the interplay between gravity, dark matter, and dark energy. Observations of distant supernovas, particularly Type I explosions, have shown that the universe's expansion is accelerating due to the influence of dark energy. This discovery has led to several competing scenarios for the universe's end. 1. The Big Freeze. If dark energy continues to dominate, the universe will expand forever. Galaxies will drift further apart, and star formation will cease as interstellar gas is depleted. In this scenario, supernovas will become increasingly rare, and the cosmos will gradually fade into a cold, dark state. 2. The Big Crunch. If dark energy reverses or weakens, gravity could pull the universe back together. Galaxies, stars, and eventually all matter would collapse into a singularity, ending in a cataclysmic implosion. 3. The Big Rip. In this extreme scenario, dark energy grows stronger over time, tearing apart galaxies, stars, and even atoms. The universe would disintegrate entirely, leaving nothing but a void. 4. The Eternal Universe. If dark energy stabilizes, the universe could reach a steady state where expansion slows but does not stop. In this case, supernova remnants and other cosmic structures would persist indefinitely. Supernovas as cosmic timekeepers. Supernovas provide critical data for understanding these scenarios. By studying their light curves and redshifts, astronomers can trace the history of the universe's expansion and refine models of dark energy. The regularity of Type Ia supernovae makes them reliable cosmic clocks, allowing scientists to measure the universe's age and predict its future trajectory. For example, by observing supernovas at different distances, researchers can map the rate of cosmic expansion over billions of years. These measurements have revealed that the universe's expansion began accelerating roughly 5 billion years ago, a finding that fundamentally changed our understanding of cosmology. The decline of supernovas. In all possible futures, the frequency of supernovas will decline as the universe ages. Star formation will slow as galaxies exhaust their supplies of gas, and the massive stars that fuel core collapse supernovas will become increasingly rare. Eventually, even Type Ia supernovas will fade into history as white dwarfs cool and binary systems become inactive. The timeline for this decline is vast. Core collapse supernovas may cease within 10 billion years, while Type Ia supernovas could persist for trillions of years. However, the universe will eventually enter a phase where no new supernovas occur, leaving only their remnants as echoes of a more dynamic era. The role of supernova remnants. Even as new supernovas vanish, their remnants will continue to influence the cosmos. Neutron stars and black holes, formed in the aftermath of supernovae, will persist for billions or even trillions of years. These objects will shape the motion of nearby remnants, occasionally colliding or merging to create brief flashes of activity. In the far future, black holes may dominate the universe, swallowing remaining matter and radiating faint energy through Hawking radiation. While these events will be rare, they will represent the last vestiges of dynamism in a fading cosmos. Supernovas and the cycle of creation. Despite their eventual decline, supernovas symbolize the universe's capacity for renewal. They remind us that creation and destruction are intertwined, and that even the most violent events can give rise to new complexity. The heavy elements produced in supernovas will continue to shape the universe's structure, providing the foundation for whatever phenomena emerge in its later stages. In speculative scenarios, advanced civilizations might find ways to harness the energy and resources of supernova remnants, extending the legacy of these explosions. Such efforts could transform the remnants of stellar death into tools for survival and exploration, ensuring that the story of the universe remains one of possibility and resilience. Philosophical reflections on the end. The decline of supernovas raises profound questions about the nature of time, existence, and meaning. As the universe moves towards stillness, what becomes of the stories written in its stars? Supernovas, with their brilliance and brevity, serve as reminders that even fleeting moments can leave lasting impacts. The end of supernovas also invites reflection on the concept of endings themselves. In a cosmos where even the most powerful events fade into silence, the persistence of their legacy, elements, remnants, and influence underscores the interconnectedness of all things. This perspective shifts the focus from loss to transformation, emphasizing the enduring nature of change. The ultimate mystery. While supernovas illuminate the universe's evolution, they also deepen its mysteries. How do they interact with dark energy? What role might they play in the final stages of the cosmos? These questions, and others yet unimagined, ensure that the study of supernovas will remain central to our understanding of the universe. A future beyond the stars. Even as the universe grows darker, the knowledge gained from studying supernovas will endure. These explosions, which bridge the cosmos's past and future, remind us of the beauty and power inherent in transformation. They teach us that even in the face of entropy, the universe is a place of infinite wonder, where every moment carries the potential for discovery. If you like the video, don't forget to subscribe to the channel. This helps my work a lot and shows me that you are interested in me continuing to produce more videos.